Teste 1, 2, 3, 3, 4, 5. 1, 2, 3, 4, 5, 6. Teste 1, 2, 3. Teste, patati patatá. 1, 2, 3, 4. 4, 3, 2, 1. 1, 2, 3. 1 barco, 2 barcos, 3 barcos. Não, o terceiro já não está cá. Mas pronto, estão só dois. 1, 2, 3, 4, 5, 6. 1, 2, 3. Uhum. Ah, é.
Isso fez ontem também. Pois, assim ontem foi tipo às 10 da noite e nós só não fizemos para não. Pois, sim, é melhor assim um botãozinho assim. Sim. Acho que não sabe, não fizeste bem.
Meu Deus. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5. Está ligado. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. 3, 2, 1. 1, 2, 3, 4. Está fixe?
Por acaso não reparei. Mas eu também falo. Mesmo com isto ligado estava a apanhar bem. Assim, com isto para baixo estava bastante. Portanto, não sei, por acaso não sei se isso interfere com isto. A gente quer que ele ande aqui, não é? Os médicos, 30, mas mesmo com aquele com o dial para baixo, esse que acabou de subir, o segundo. Então eu gostei para isso. Sim, realmente isto estava em pré-feita. Está aqui as indicações todas. Eu não sei se. Eu acho que a parte do áudio nesta sala não é o mais importante. Sim. Eu só tinha realmente essas indicações porque eu realmente não sabia se esta sala ia ter um técnico. Eu sei que fosse só nas salas maiores. Pronto, estou livre para estas 3 salas. Não, é fora, são estas 3. Sim. Técnico pode cá ficar. Não está bem meio. É melhor porquê? Depois este fader funciona. Ok, sim. Por mim dá tudo bem. Eu não. Sim. Eu só não tenho isso. Não sou eu que vou editar os vídeos. Só um bocadinho só para ver aqui no OBS como é que está. Se está para ver.
1, 2, 3, 4. Teste. 1, 2, 3. Olá, boa tarde, boa noite. 1, 2, 3, 4. Splash Cascais. Twig, Huawei, Prime Video. Sei lá, está ali uma coisa com música. Não sei se aquilo é música. Pronto. Uma coluna, 2 colunas.
Está bom porque ele realmente sabe falar para o microfone. A maior parte dos speakers não vão. Sim. Há as duas coisas, ou afastar muito ou chamar de comida. O meio dos microfones estão ali assim. E há alguns que. Depois, às vezes, os microfones vai ficar com perguntas. Certo. Ok. Então o micro fica ali. Se alguém quiser uma perguntinha, vai lá, fala. Agora vamos ver este aqui. Este aqui está mais fraquinho. Ora, bebebel. Este. Já não te lembravas como é que era? Ora, então, bebebel. Este agora, o de mão está bom. Vamos fazer aqui uma perguntinha. Está muito bom. Bababá. Ora, um bocadinho menos. E agora vamos baixar aqui um bocadinho o púlpito. Assim. Esta onda assim. Pronto. Olha, só favor, já que aqui estás. Porque eu quero fazer uma pergunta. E ando aqui nos menos 30. Está muito bom.
Ora, boa tarde. Programação 1, programação 2. Olha, até estou a falar tipo afastado.
Isso. Está ótimo.
1, 2, 3, 4.
Ora, só vou só baixar aqui ligeiramente, aqui assim, e pronto. Este pode ficar já ali. Fica já ali. Se calhar, mete no mute, não sei. Não, porque as pessoas não conseguem. E o técnico consegue falar. Depois, ok, Karina, sim. Sim, está bem. Mas pronto, Não, é justo, sim. Eu esqueci do botão do mute. É no channel mute. É sim, se tem de tirar o mute, Não, eu sei, sim. Mas eu esqueci do botão do mute, claro. Só pronto. Queria falar contigo, então se lá pilhas. Sim. este ecrã vai ser só para streaming e record, porque ali vai ser só mesmo só os slides. No máximo dos máximos. Sim, não vai ser só os slides e esta coisa de quando que passar de uma tal para a outra.
E se existe aqui um computador, a aquisição tiver som?
Como assim?
Ou seja, se numa apresentação, para um vídeo, tiver som.
Em princípio, eles teriam avisado, mas eu acho que não vai acontecer.
Em todo o caso, aquele carro. Aquele carro vai aqui.
Sim, é HDMI, sim, via.
Depois sai deste computador para ali. Em todo o caso, o som, este PC é este.
Sim, é esse, é um 7
É esse. Já está ligado, por acaso.
Sim, eles não meteram pre-fader nesse, meteram nesse evento. E
Só as coisas não estão ligadas, nesse caso.
sim.
Mas isso também.
E há um momento, porque eu realmente não sei o que é que se passa com estas
Se chega a uma coisa.
Ok.
Talvez mais nesta. Esta
Foi esta, foi. Ainda por cima, ontem nós estávamos aqui de estar, eu estava literalmente ao lado da coluna.
Esse é o mau contacto. Porque no caso, dava-se então ligar aquele e eu via-se o som do vídeo.
Sim, de facto. Sim.
Uma coisa que eu faço sempre antes de cada hora de ligar o computador é perguntar se eles têm vídeos com som ou se têm músicas para passar.
Ok.
Se fica logo dentro de uma nossa.
Sim, podemos perguntar isso, sim. Porque realmente alguns oradores podem não ter visto as instruções, porque realmente nas instruções estava lá a dizer que se tiverem algum vídeo avisar.
Sabem, isto são instruções e.
Sim, de facto. Também vamos ter que ter cuidado porque, por exemplo, quando eles ligarem o computador, eles são muito impacientes e isto ainda demora cerca de 10 segundos. Eles estiverem sempre lá a meter e a tirar e não sei o
Não
que.
tem imagem.
Porque ainda demora um bocadinho a recebermos a imagem do
Então
computador.
tiram uma grande mira.
Sim.
Já está a funcionar, vou tirar.
Pois,
E tem que esperar um bocadinho. Então está bem. Mas aqui está orientado.
Sim. Força. go to it. And this speaker, I talked with him. This speaker will be off the entire session. That one is it will be on because this one is the broken one.
Yesterday we tested it out, it was working fine.
We tested out like 5 minutes ago.
Oh yeah?
It was a bit broken.
Oh, yeah, sure. Yeah, fine.
Ok.
Yeah, that's fine.
Não, estava só a perguntar em relação àquela situação do áudio que disse, em princípio não vai ter.
Mas caso a música.
Sim. Mas caso tenha, é só o orador dizer que quer exportar o vídeo por HDMI.
Pois era o som.
Sim.
Eu se calhar ligava aquela já. Ficava
Ok.
ligado.
Sim.
So how it works is that SE line goes to capture card,
Yeah.
and capture card can also transfer sound.
Mm-hmm.
So it goes when we have configured. Why is this picking up?
I don't know, it was in top transition flag.
Oh,
It should be like in the break transition flag. I mean,
No, here.
okay, yeah.
Of course, you got it. Yeah, I got it.
Okay, yeah.
Okay.
Sorry.
First speak this setup.
あ、いました。
For this, first.
なんかたまに
Yeah. Sorry. I
あ
thought
よかった
it
です
was
いや
the
たまにちょっと HDMI 経由じゃなくてこうタイプ C じゃないと聞かないとき
There we go.
That is
4 by 3.
Yeah, it's fine.
Yeah? Okay. Good.
Yeah, that's what I'm trying, but. Okay. So it's not like this. Hello? Ah, yes. Okay. Well, so I'm the chair of PPTP. Thank you very much for attending PPTP. Okay. We have 13 presentations, the regular papers during these 2 days. We have 2 invited speakers, Delia and Maribel. Okay. For the talk of Maribel Fernandez tomorrow, is going to be in another room, the room of Lobster. Okay. And there's a problem in the program where it says that Maribel is going to be in 2 places at the same time. Okay. So just be aware that she can be only in 1 place and it's going to be in Lobster, the other room. Okay. And we have also a paper today about the 10-year award. So I'm not so sure if the speaker is here. Okay, I will look for him. Okay, so it's the other activity that we have. Okay, and Michael Janus is going to chair this first session with 3 papers. So thank you very much. Okay, and I think that's all. So thank you for attending, and I hope you enjoy PPDP. Okay. And remember that all the talks of all the events are going to be recorded, okay? So when you have questions, just wait for the microphone, okay?
Okay, thank you very much for the introduction. So I'm Michael Hanus, and I will chair the first session, and we already see here the title of the first session, Calculus of Delayed Reduction, and Emma will present the paper.
All right, thank you. So our calculus is called the Calculus of Delayed Reductions, and this presentation will be about this. It's an extension of call by push value. Call by push value is a calculus designed by Paul Levy. The basic theory of this calculus is that we distinguish terms into 2 distinct sets. Computations, something that does, and values, something that is. It was originally proposed to model the call by name and call by value sections of the lambda calculus, but it doesn't actually model small step semantics correctly. Instead, we present CDR, our calculus of delayed reductions, which can be seen as a simplification of call by push value, which changes how substitution works. We will show in this presentation that we can interpret call by name and call by value into our CDR and show that reductions and types are preserved. We also introduce Herbulin and Currian's lambda bar mu utility calculus, and we can interpret our calculus delayed reductions into that, motivated by its natural modeling of call by name and call by value. First off, a quick refresher on the lambda calculus and call by name and call by value. Lambda terms have this subset called values, and then just regular terms. You'll notice that these values contain variables and abstractions. We'll call these lambda values from now on to distinguish between these and other calculi's definitions of values. Beta reduction just contracts an abstraction and an application, and in the regular lambda calculus, we can reduce everywhere. Call by name restricts the contexts to just the left-hand side of an application. This can be seen as lazy evaluation, where we don't evaluate the argument before applying it. And call by value reduction reduces on the left-hand side of an application, then the right-hand side. Notice that we can only beta reduce when the right-hand side is a value. So this can be seen as a kind of a form of strict evaluation, where we evaluate the argument before we pass it in. Call by push value is an extension of this lambda calculus. So we have these variables, these abstractions, and these applications. But we also have some extra syntax. We have this thunked computation, which is what these curly brackets are around in a value. We can have a forced value, which is what this bang does. We can return a value, or we can sequence 2 computations together. Notice that these values, this distinct set of values, are not lambda values. The abstractions here are actually considered as computations. The reduction rules are as follows. We just have our regular contraction, which by design and syntactically has to contract values, because you can't have a computation on the right-hand side of an application. We have this unblocking, this forcing of a thunk. And then we have this returning or forcing, where if we sequence a returned value next to a second sequence computation, we substitute it in. So essentially, sequencing reduces computations until they are returned. Valuation context, we can reduce on the left-hand side of an application and in the first sequenced computation. We can only reduce computations and never values. Notice here that thunking itself does not actually halt reduction. By the reduction rules and the contexts, we can never actually reduce anything where a thunk could be anyway. We never reduce a value. So we can never reduce on the right-hand side of an application, we can never reduce underneath a ret, and we can never reduce, basically those, and we can never reduce under a force either. So actually, all thunking does is kind of syntactically mark where values are, change a computation into a value. It doesn't actually affect reduction in any kind of way itself. And in fact, even more than that, it's more just something to give us these distinct sets of types, these type markers. The call by push value types are a bit more interesting. We have these syntax markers U for value types and F for computation types. Other than that, we have regular simply typed lambda calculus type variables and arrow types. Notice that these arrow types, by the definition of how an application works, we have to have a computation on the left and a value on the right. So we have value type to computation type. We have a context of variables, but these have to match to value types because variables can only be values. And we have all our type assignments. We have our regular axioms, our regular applications, and our regular abstractions. Thunking, you see here, doesn't take anything else other than just a computation type A and shoves a U on it, just as we shove it into a thunk. We have our forcing, which just takes a U and pops it off, which is exactly how it would do an unblocking here. We have a returning, which just shoves an F on, but the sequencing here is what makes the returning a little bit more interesting than the thunking here, because it actually has some kind of interesting semantics to it where we have to pop the X into the typing of N in the second sequence. So more importantly, we want to interpret the different reduction strategies of the lambda calculus in call by push value. For the call by value lambda calculus, what we do is we return our lambda values, our variables and our abstractions, and then in application we sequence the first computation and then the second computation. And because of the typing, we have to then force X in the third sequenced computation. This is kind of a shorthand for sequencing multiple computations together. If we can't have X, Y just regularly because that doesn't fit our syntax of a computation on the left-hand side, which also is why we can't return just a lambda, because lambdas are computations in call by push value. So we actually have to thunk that. And we have to use the returns here instead of just returning a regular lambda, because that is a computation type, because then we would never halt reduction in our sequencing. Unfortunately, this is only respected by equality in reduction under call by value in the lambda calculus. So basically, if you have a lambda term that runs under call by value to another lambda term, the interpretation of it runs to another value which the original, I'm sorry, I'm not explaining this very well. So we have a lambda value m that runs under call by value to a term n. Then the interpretation of m might not run directly to n. It might run to a term that n will eventually run to. So the reduction of the interpretation of m might not reduce into n. Call by name is in fact even more complicated in how it's related. The call by name interpretation of lambda terms and call by push value by Levy forces a variable, just returns a regular abstraction and just a regular application with the thunk marker on n. This doesn't use return or sequencing. It looks very, very similar to how the lambda calculus is actually structured. However, this doesn't actually respect reduction at all. Consider a self-returning term, lambda x.xx applied to itself. The interpretation of this is lambda x.x bang thunk applied to the thunk of x bang, which, if you reduce it twice here, you get this explosion of force-in thunk pairs. And this will just keep reducing and exploding into force thunk pairs. And because of the evaluation context, we can never reduce any of these force thunk pairs. We have to keep applying it, and it will just completely explode. So what Levy does is he adds this other interpretation rule, which means that we can relate any lambda term to itself with any number of force thunk pairs on top of it. This new interpretation allows reduction, or allows us to interpret, essentially, we have the interpretation of a term can reduce to anything. If a term reduces under call by name to another term, then their interpretations may reduce to each other, to any element in the set of its interpretation. But fortunately, this means that the interpretation is not even a function, it's a set of equivalence classes. It's just a relation, which is a lot less powerful than a function. So our solution here is to change term substitution so we don't get this explosion of force thunk pairs. Our calculus of delayed reductions is call by push value, essentially, but we prevent any forcing of thunks or thunking of forces. So here, the changes we have to our syntax is that we can't have a thunk of a forced variable, and we can't force anything that isn't a variable, because other values are just thunks. Substitution is changed so that we automatically reduce force thunk pairs in the substitution itself. So if we have a forced variable and we want to substitute a thunk term in it, we immediately strip off the thunks and the forces. This means that we can remove our unblocking rule. And evaluation contexts are before. This won't actually change any of the reduction strategies any of the reduction in call by push value, because as before, thunking here doesn't actually change reduction itself. It was just the evaluation rules and the contexts that affected how reduction works in call by push value. So this itself isn't going to affect how any terms can reduce. Type assignment here, we optimize a little as well, because we know now that we can never force anything but a variable, and we can never thunk anything but not a forced variable. So here's where the money shot is. We have call by value and call by name. So the original Levy's call by name has all these returns, but this has only respected by equality. We use pattern matching instead to make it actually respect proper reduction. So we pattern match on the left-hand side of an application for lambda values. And if we have a lambda value, we can immediately just remove part of the sequencing. Because if we had Zn and we interpreted it in Levy's, then we'd have x equals the return of z and y equals n, which we could immediately reduce to this. But so instead, we just immediately return this. And the same with lambdas. Call by name, Levy's interpretation preserved the structure of these, but didn't do any kind of pattern matching or optimization on this, which we do, just considering that the right-hand side is a variable. So this essentially means that we have to do this so that we don't have any force thunk pairs. Because if we were to have interpret n as x here, then we would have m applied to the thunk of force of x, which we can't have. These encodings do respect reduction of call by value and call by name. The new substitution is needed, though, to the call by name value, as you remember from the self-returning term. So what we also have here is the calculus lambda bar mu mu tilde. This is Herbert and Curian's calculus that models call by name and call by value reduction in a different way to call by push value. This has three categories of expressions. It has commands, which has a term on the left-hand side and an environment on the right-hand side. It can also be seen as a kind of abstract machine, as we'll see later. Terms are just variables and abstractions, but we also have this mu abstraction, which takes a context and returns a command. We have an environment, which can be an environment variable, which we denote by Greek letters here. It could be a stack of a term onto another environment, or it can be this mu tilde abstraction, which takes a term and returns a command. We have our reduction rules. So the mu reduction rule, as we can see, just kind of does what we'd expect. It takes, if a mu is in the left-hand side of a command, it will take the right-hand side, it will substitute the right-hand side's environment, and same for mu tilde, but in the reverse. The interesting one here is how lambda is done. So if we have a lambda term in the left-hand side of a context and a stack in the right-hand side, we don't immediately substitute it, as you might think. We, in fact, just pop the term off the stack and put this kind of mu tilde, so we create this mu tilde term through lambda reduction in the right-hand side, which, if we reduce it immediately, will apply T2 to mu tilde. So we can see a critical pair here is if we have a mu on the left-hand side and a mu tilde on the right-hand side. Which one do you reduce first? And in fact, both of these reductions are not confluent, so you might get a different result depending on which one you reduce first, which is why it's so interesting here. The rule lambda here, because it doesn't immediately reduce, we can actually see the strength here to model both call by name and call by value reduction. So we have lambda mu mu tilde values, which kind of correspond to lambda values, variables and abstractions, and we have what we call stacks, which has an environment variable and this t on top of a term on top of an environment, which I'm calling a stack as well. So a stack could just be kind of a finite number of terms on top of variables. Call by name reduction limits the mu reduction rule to stacks. So say we had a critical pair of mu and mu tilde, then we will always run the mu tilde in call by name reduction of the lambda bar mu mu tilde calculus. Call by value does the opposite. We limit the mu tilde rule. So if we have a critical pair of a mu on the left-hand side and a mu tilde on the right-hand side, we will always run the mu. Both of these reduction strategies only run terms and never context. We can only run in the left-hand side of a command or under a mu abstraction in both of these reduction strategies. So say we had a lambda abstraction and we expanded that into popping the term into the left-hand side and putting a mu tilde in the right-hand side, then our call by value reduction, we would reduce our term in the left-hand side until it produced one of these values, and then we would apply our mu tilde. And then if we had call by name, we just immediately run the mu tilde so that we'd substitute it in. Our type assignment for the lambda bar mu mu tilde can be seen as a kind of variation of the implicative classical logic, so Gensen's sequent calculus. Indeed, we can type Peirce's law, and this is the lambda bar mu utility term that represents it. We just have, so the cut rule here is what really kind of exemplifies this correlation between them. But more interestingly, we can now interpret our calculus of delayed reductions into lambda bar mu utility, which kind of relates the call by name and the call by value reduction strategies between them. So regularly, we basically interpret variables as variables. We get rid of all the forcing and thunk markers and the ret marker. The more interesting thing here is what we do in terms of application and sequencing, which, according to our reduction rules in the calculus of delayed reductions, that's what actually produces new results. This is what our base reduction rules are. So, interpreting an application, we put the left-hand side of an application in the left-hand side of a command, and we put our value on a stack. For sequencing, we put our first sequence in the left-hand side of a command to run, and then we put our second sequence under a mutility abstraction in the right-hand side, ready to be substituted. So the left-hand side is ready to be substituted for x once it's reduced. This reduction, modeling of the reduction rules of CDR, actually takes place in the call by name reduction of lambda bar mu mutility, where we can only reduce mu's when we have not a mutility on the other side. This is because to reduce application here immediately, we have to be able to reduce our mutilities immediately. Otherwise, we'd run our value, which might be a thunked computation, which we do not want to run. We want to immediately substitute it. For type assignment, we also just get rid of all our type markers for thunks and forces. So we can also, Levy also explains an abstract machine for call by push value, this CK machine. And this is kind of what originally brought us to comparing call by push value and the lambda bar mu utility calculus in the first place. Essentially, we are going to define an evaluation of like an abstract machine state as this pair of a call by push value term and an evaluation stack. You can kind of notice a kind of similarity between the terms of lambda bar mu utility and these evaluation stacks. So this kind of just has the original ones, where we can apply a value that's popped on an evaluation stack to an abstraction. If we sequence something, we can pop the sequenced value, the sequence computation along with the substituted variable onto the stack. Returning pops this special syntax off the stack. Application just pops the value on the stack. But notice in the last rule that forcing and thunking doesn't interact with the stack whatsoever. It's just this kind of rule that does itself. It's just this syntactic rule to get rid of these markers itself. It doesn't interact with any kind of evaluation context. So we can use lambda bar mu utility as a stack machine for calculus, for call by push value. So we can interpret these evaluation stacks as a lambda bar mu utility environment. Our regular stack is just some kind of variable. We have our stacks of call by push value values as a lambda bar mu utility stack. But here's where the interesting one is. X equals this context hole sequenced with n actually is a mutility, which kind of makes sense. We have an environment which takes a variable and returns a command which runs another sort mutation in the rest of the stack, which is exactly what mutility does. And then we just have our regular stacks, which substituting, basically copying this syntax here and using the original interpretations we made from CDR into the lambda Barmy mutility calculus. It was this exact similarity that we can see here that originally was the inspiration for our entire paper, for us examining how call by push value works in the lambda Barmy mutility calculus and realizing that we don't really have a way to model this forcing and thunking, which got us interested in why that was necessary in the first place. We can show that if the CK stack runs, then runs to another CK stack, then their interpretations do eventually run to each other. So this does respect reduction in that way. So in conclusion, we've defined a calculus based on Levy's definition of call by push value. We've shown that tweaking term substitution and using pattern matching in the interpretations, the call by name and call by value reduction in the lambda calculus are respected by reduction, not just an interpretation of it or by equality. We established strong relation with lambda Barmy mutility, showing using this CK machine approach. And because to model call by push value reduction in lambda Barmy mutility, we need to use the call by name fragment of lambda Barmy mutility, which show that call by push value reduction is actually based on the call by name reduction. Since then, we've added call by value reduction to call by push value, adding a let construct, and we gave the lambda Barmy mutility the call by push value treatment, and showed a strong relation between the two, mapping call by name to the call by name fragment of the call by push value to call by name and lambda Barmy mutility, and vice versa for call by value. Next, we will see if thunking, forcing, and return are really necessary. Questions?
The one is about in your call by push value framework, why you decide to keep variables as values?
So you're suggesting that we could have put variables as computations instead, perhaps?
I mean, why do you need to do that?
Yeah, I mean, why do we need to have the distinct sets of values and computations in the first place? That's an interesting thought. I think that we wanted to keep as close to call by push value as possible, the syntax of that, changing call by push value as little as possible so that we could get the results that we needed, which was correct call by name reduction. But you're right, we could create an entirely new calculus which gets rid of these distinct sets of terms and just has a subset like the lambda calculus does of values.
And another question is, so now that you have a good correspondence by using your new translations, have you used these translations to infer or derive properties from for call by name and call by value from the ones for call by push value or vice versa?
Not yet, I don't think so.
I don't understand the question.
So the question is, now that you have a good correspondence between reduction in call by name and call by value and call by push value, do you use this correspondence to get deep results of preservation of some kind of property? For example, you can infer different property, for example, confluence. Let's take an easy one. You can infer confluence for call by name and call by value using confluence for call by push value. That's just an example.
So first of all, the confluence issue doesn't exist in call by push value because you can always only reduce one thing. There's only and there are sorry, there are no diverging reduction paths in call by push value, and so the extension that we have when we add call by value, that's when we have to look at confluence. Now we have an extended reduction system with diverging paths, and we can do that. So I think the properties that Levy shows for his interpretations are very shallow. He doesn't really investigate anything deeper. So what the paper basically does, it fixes that approach. I think it's very. I think the strength of the paper is that with very minor changes, not really. For example, Levy talks a lot about semantics in his paper. That's all preserved. That we don't touch that at all. The only thing we do is change the substitution, and that's everything works. Yeah.
Okay, other questions? Oh, yeah.
Yes. You changed both the substitution and the translation to call by name and call by push value. How do those things interact? So do you still have the property that if you have an open term, then substitute and translate, it's the same as translating first and then substituting?
Yes, yeah. So we do in the paper prove that substitution itself is preserved from, the interpretations in the lambda calculus. So substitution in the lambda calculus is substitution in call by push value, even with this new substitution rule. So we do get all those nice properties that you do get from, like our interpretation is not like, just saying, oh, well, it's this and then it's this and then, it kind of works. No, it is a proper, nice interpretation here that is luckily one-to-one now, and other than this kind of set of equivalence classes.
Okay, so thanks again for the discussion. And now we switch to the next talk, so please.
Sorry, 16 by 9, right?
Yeah, 60 by 9, sorry.
No.
Thank you.
Okay, so everything works. So nice. The next talk has a very long title. I want to avoid to say it again, and therefore just Kazuki, you can start.
Yeah, so hi everyone. I'm Kazuki Ikemori from Tokyo Institute of Technology. So I will talk about the equivalence of express power between Lebed effect calculus. So let me first start with some background. Effect handlers with first-class labels and control operator with first-class labels are used in several practical programming language for abstractions of computational effects. For example, Coca and TabLift have effect handler with first-class labels. And Haskell and Racket have a control operator with first-class labels. So labeled effect handlers and labeled control operator have similar functionality. This similarity has already been used to understand and implement the functionality of one from the other. For example, Xerov et al. Has been used to implement labeled algebraic effects in OCaml using labeled control operators. So we concerned with the equivalence of express power between labeled effect calculus. To show the equivalence of express power between labeled effect calculus, between labeled effect handlers and labeled control operators, we aim to define translation that preserve type and meaning between the two types of calculi. If the equivalence of express power between labeled effect calculi can be shown, there are two benefits. The first one is that we can implement one labeled feature using the other. The second one is that we can apply the theoretical property of one labeled calculus to the other. In previous research, the equivalence of excess power between effect handlers and control operators is shown by defining macro translations. Forster et al. Defined macro translations that preserve meanings only. Pirog et al. Defined macro translations that preserves both meaning and types. We can consider two approaches that are direct approach and incremental approach. In the next slide, we first explain direct approach. So one possible approach is to directly define macro translations of the calculi with first-class labels by extending the macro translations of previous research. However, a gap between the first-class labeled effect calculi and plain effective calculi. To bridge this gap, we need to address many issues. So we take incremental approach to define the macro translation between effect handlers with labels and control operators with labels. The first step is to define the calculus of effect handlers with second-class static labels and calculus of control operator with second-class static labels, respectively. In this step, we first show the effect safety of the control operator with second-class labels, which has not been shown in previous research. We then define these macro translations between the two and show that they preserve types and meanings. The second step is to define the calculus of effect handler with second-class generative labels and the calculus of control operators with second-class generative labels, respectively. In this step, we first address name escaping program using lexical scoping. This technique was used for object effect handlers, but not for control operators. So we apply this technique to control operator and define a type system for control operators to prevent name escaping. We then define macro translations and show that they preserve types and meaning. The overview of our research is shown in this slide. So we formalized 4 calculi covering all combinations of effect handlers, control operators, and static generative labels, and show the equivalence of expressive power between them. Preparation for extension to the first-class labels can be done by this work. We explain the details of each step in the following slide, and we focus on static labels because generative labels is very similar to static one. So we first formalize the lambda FL that has effect handlers with static labels. These consist of labeled operations and labeled handlers. Operations are for performing computational effect, and the handler gives interpretations for these operations. Labels are used for associating an operation with a specific handler. This calculus is based on the earlier iteration on F programming language that has algebraic effect handler with labels, and we prove its type soundness. Yes, so let us look at the example of this calculus. First, the operation called do L is performed. L represents static labels. The program execution is then shifted to the inner handler with the corresponding label L. At this time, the program with the blue background is bound to the variable R as a continuation. Then by applying continuation R to 1, the program is resumed from the point where the operation was performed. Hence, the value 1 is bound to the variable state 1. Next, the operation called do L prime is performed. The program execution is then shifted to the outer handler with the corresponding label L. At this point, the program with a red background is bound to variable R as a continuation. Then by applying continuation R, to 2, the program is resumed from the point where the operation was performed. Hence, the value 2 is bound to the variable state 2. Finally, the result of war program is 3. The type system of effect handled with static labels can guarantee that every operation is handled by a handler with a corresponding label using the effect system. The typing judgment of effect handlers with static labels states that expression E has type tau and the type variable environment delta, variable environment gamma, and label environment sigma. And the may perform effect row. By determining whether row is empty or not, it can be determined whether all operations are handled. So we prove that our calculus of effect handler with static labels meets effect safety. For example, we can statically judge that all operations in this expression are handled because the effects of this expression are empty. On the other hand, we can statically judge that this expression contains an operation that is not handled because the effects of this expression are not empty. Okay, let's go to the next slide. So we next formulate the lambda del L that has limited control operator with static labels. Limited control operators consist of two operators, shift 0 and dollar. Shift 0 operator is used for capturing a continuation, and the dollar operator is used for delimiting a continuation. Labels are for associating a shift with specific dollar. And we prove its type soundness. Let us look at the example of these calculus. First, we define a reader 1 and reader 2 functions that have shift 0 operator to get the value from a reader state, read-only state. The shift 0 operator of the body of the reader 1 function captures a continuation up to the inner dollar with a red label. It is evaluated to value 1. On the other hand, the shift 0 operator of the body of the reader 2 function captures a continuation up to the outer dollar operator with blue 1. It is evaluated to value 2. Finally, the result of war program is 3. Yes, so in the next slide, we explain why is effect safety important for defining typed macro translation. A typed macro translation preserves effect safety, so the existence of the effect safety of source and target calculi is necessary to define typed macro translation. However, type systems of previous research for labeled control operators do not meet effect safety because these type systems do not have effect system. Hence, it is not possible to translate a labeled control operator in a type system of previous research to a labeled effect handler in a type system with effect safety. Since type system of previous research do not have effect safety, these type safety cannot ensure any shift operator is surrounded by dollar operator with a corresponding label. For example, this is effect unsafe program. This program is effect unsafe because this shift operator with label L is not surrounded by a dollar with label L. However, the type system in previous research cannot check for shift 0 operator that is not surrounded by dollar operator with the corresponding label L. To address this issue, we define an effect system of control operator with labels. So our type system can ensure effect safety for control operator with labels. We prove that our calculus of control operator with static labels meets effect safety. In this program, our type system can check that a shift 0 operator is surrounded by a dollar, is not surrounded by a dollar operator with a corresponding label L. So in the next slide, we talk about typed translation. We define the translations between Reject effect handler with static labels and delimited control operator with static labels. And we prove the type and meaning preservation property of them. Let me explain the translation from lambda del to lambda FL. The translation is represented as a sharing bracket and extends Pirog's macro translation with static labels. The extended translation is not so hard, associating shift and data operation with static labels. A data operator with a label L is translated to a handler expression with the label L. This should intuitively make sense as a handler and the data operator play a similar role, namely to delimit the current continuation. The operation close past the continuation K to the operation's argument F. A shift operation with the label L is translated to a do operation with label L. The operation received a function that takes a continuation, which is translated to from the body of the shift operator. Yes, so let me explain the translation from lambda FL to lambda del L. This is opposite direction. The translation is represented as floor bracket and extends Pirog's macro translation with static labels. The extended translation is also not so hard, associating operations and handler expression with static labels. A handler expression with label L is translated to a shift operator with label L. This should intuitively make sense as a handler and the data operator play a similar role, namely to delimit the current continuation. The operation close of the handler is translated to a lambda term and applied to the data operator. A do operation with label L is translated to a shift operator with label L. This should also intuitively make sense as a do operation and a shift operator play a similar role, named to introduce an effect. The expression lambda x dot kxh in shift 0 operator represent the delimited continuation of the operation call, including the surrounding handler h. Okay, so we explained the Reject effect handlers with generative labels. So we format the lambda f L plus eta that has effect handler with generative labels. This calculus is extended by lambda f L that has effect handlers with static labels. Generative labels are generated at runtime. Lexical scoping prevents labels from escaping scope. By generating labels at runtime, users do not need to know the exact number of used labels. In the program example below, when reducing the right-hand expression is to the left-hand expression, a new static label L is generated. And label eta is replaced with static label L. We next format the lambda del L plus eta that has control operator with generative labels. This calculus is extended by lambda del L that has control operator with static labels. Generative labels are generated at runtime. Lexical scoping prevents labels from escaping scoping. In the program example below, when reducing the above expression to the bottom expression, a new static label L is generated and generative label eta is replaced with static label L. So we define the translations between Reject effect handler with generative labels and delimited control operator with generative labels. And we prove the type and meaning preservation property of them. Let me explain the translation from lambda del L plus eta to lambda f L plus eta. The translation is represented as cell bracket. the definition of the translation from lambda del L plus eta to lambda L plus eta is almost the same as the translation for static labels. The only difference between translations of static labels and generative labels is that static labels are replaced with generative labels. The translation from lambda del L plus eta to lambda FL plus eta is represented as floor bracket. The definition of the translation is again almost the same as the translation for static labels. We just use generative labels instead of static ones. In this work, we can define 4 calculi covering all combinations of effect handler, control operators, and static generative labels, and define typed macro translations between the corresponding calculi. So our original research goal is to define translations between first-class labeled effectful calculi. The first-class label allow us to use labels in more flexible way. For example, we can implement ML-style mutable reference cell using first-class labels. As I said at the first slide, COCA has effect handlers with first-class labels and formalization of effect handler with first-class labels. COCA avoid name escaping using rank 2 polymorphism. So I would like to extend our calculi with first-class labels using this technique. To summarize, we formalize 4 calculi covering all combinations of effect handlers, control operators, and static generative labels, and show the equivalence of express power through defining typed macro translation between the corresponding calculi. Thank you for your attention.
So, are there any questions? So, please.
Hi, thanks for your talk. My question is, do you expect there is any specific obstacle for proving the translation with first-class labels?
Yes. So I expect extend the second-class type macro translation to first-class macro translation is not so hard because so this work is almost completely prepared to the extend the second-class translation to first-class translation. So I think the most difficult part is apply to higher, so second-rank polymorphism to the type macro translation. Yes, so I think.
So, are there further questions? Yes.
So for the to study the limited control, the limited operations, did you look at other formalisms, like for example the Laptopamine-Matilda calculus? The one we had in our paper. That's based on classical logic, and you can express the limited continuations in there. It's a very elegant way to do that.
Yeah, if you have looked into other formalisms, like the paper they had.
So there's the Courier et Herbelin 2001 paper.
Yeah.
So that's a calculus in which you can express the limited continuations directly.
Okay, I see.
So there is another calculus
Yeah.
where they can express the limited control continuations, whether you have looked into those papers or whether you know those papers. If not, it will be a good, a very good suggestion.
Yeah, so I haven't not looked at this paper. So
Yeah, so because I see that you use a CPS translation. So you can avoid that if you go to that kind of calculus.
Yeah. I see. Yes. Okay. Thank you so much. So I'm going to look this paper. Thank you.
Okay, so I have also a question. So you showed these interesting equivalences, and some part of this conference is also related to the practice of declarative programming. So are there also practical consequences of this work? So
practical. So sorry.
or how you can use it? So these results are there?
So you mean so my work can be applied to the practical programming.
Yeah.
So yes. So this is my long-term goal. So I would like to make a programming language using these macro translations. So I think the difficult part is in current formalization is subtyping over the effect typing. So it is very problematic. This is a problematic situation. So the typing inference. And so how to address this issue is my current issue.
Okay.
May I add one thing? So one of the point is So one of his point is to use macro translation. So the almost the syntactically you can convert a program from one formalization to the other. So the one of the idea is that, for example, in OCaml there's delimited continuations, but no effect translation, no effect systems. So the effect systems maybe we can introduce the effect systems in OCaml just by macro translating to realize that.
That would be interesting, yeah. Okay, then thank you very much again. And we switch to the next one.
Sorry, just a minute for the system to boot up. Not very, but I had hibernated it, so.
Sometimes the question is booting fast or hibernating. Yeah?
Yes.
It's working. I just wanted to put it in full screen.
Oh, all right. Great.
Okay, so next talk is about comprehending queries over finite maps, and Ilmar will give the talk. So.
Thank you. All right, so maybe from the title it is not completely clear, but this is a talk about general purpose programming languages interfacing with SQL databases. And you might wonder why finite maps and not relations. Well, let's start with the obligatory employees table, where you can find all the employees of a fictional company with their department and the salary depending on the value that they have for the company. And let's address the querying a database from a functional programmer's perspective. What might we want to do with this? Well, for starters, we may want to group the employees by their department. So let's suppose that we have a gamma operator that, given a relation, in this case the table employees, associates to every tuple in the relation a grouping key that in this case is just the attribute department from the original table. And what is the result of this operation, again, from a functional programmer's perspective? Well, here you have it already. It's a finite map, which is, in particular, the map that associates to each grouping key the subrelation of those tuples that match the grouping key. So for the grouping key department sales, you have the portion of the table of those employees that belong to the sales department. What do we do with a grouped relation with a finite map? For example, we might want to perform aggregation. Again, we suppose that we have a group-wise aggregation operator, this agby, that takes the result of the previous query and produces, again, a new finite map where in the value part of the map, you will have an attribute average salary, which is obtained by taking the aggregate average of the salaries in that subrelation. And yeah, that's exactly the result you would imagine. Finally, we start with this grouped and aggregated relation, and then we think, well, that there is a French buyer, so we want to obtain, we want to convert this relation using French words for the departments, and luckily we have a dictionary table that translates sales to vente and research to recherche, and then we can write another query using something that is called comprehension, that everybody surely knows from set theory, but is very used in the functional programming area as well. So we can comprehend over the key set of the query Q2, that is the values over this column, and then over the values in each of the subtables associated to a certain key. So this Q2 star X means look up into Q2 the values associated with X and return the corresponding subrelation. And then you can comprehend also over the dictionary relation. And then you will produce a table in which the department is taken from the translation table and the average salary is taken from the grouped table. And the result will be exactly what you expect, that is the French translation, also converted finally to a standard relation rather than a finite map. Why am I showing you this? The area in which I'm working is called language integrated query, and essentially this is an expression to mean the support for safe database queries integrated within a language, within a general purpose language, not by libraries, or worse, by string manipulation of SQL comments, but as a sub-language of the general purpose language itself, with all the safety characteristics that you would expect. The reason why we want it is that, for starters, it avoids the impedance mismatch, which is the difficulty of writing queries that are meant for a different language in a general purpose language. And also the fact that sometimes when we write queries by hand, they will fail at runtime even though they are statically incorrect. Also maybe because of a syntax error. This also avoids security vulnerabilities in case you were expressing your queries by string manipulation. You can optimize programs and queries together. And finally, this is basically the reason why we use general purpose languages to drive SQL databases, because in this way we can build complex dynamic queries automatically and safely in the case of language integrated query. Naturally, this appears to be a rather complex problem to match a general purpose programming language with a rather idiosyncratic declarative database language like SQL. A very successful way of managing this has been through the use of a core calculus called the nested relational calculus, which essentially identifies an overlapping portion of functional programming languages and SQL. What is it like? It's you can see it as an extension of the simply typed lambda calculus with collections. This sigma between square brackets indicates the collections of elements of type sigma. And these types can be obtained, values of these types can be obtained by using the operations in blue, which include the empty collection, the singleton collection, the union collection, and comprehension over a collection, as I've shown you in the previous slides. However, you may have immediately noticed that this sigma here is unconstrained, meaning that you can have collections of collections. So in a way, this calculus is immediately more expressive than SQL. But it's more expressive in a manageable way. And this is what we want to do with NRC queries. If their type is a flat relation, we want to manipulate them through a rewrite system and finally obtain a normal form, which we believe that will be immediately translatable to SQL through select and union all. This is because there is a result called conservativity that says if you're using nested collections in your query, but the type of your query is flat, then it means that those intermediate nested collections aren't really needed. You can normalize them away and obtain a completely flat query. When instead the query has a nested collection type, then again we normalize it, but there is another technique called shredding that allows you to slice the query in such a way that from a nested query you obtain a number of flat queries that can be run on the database. And there are two parts in blue here because originally these techniques were meant only with one collection kind, but they were extended to allow mixing sets and bags. And when you do that, you need to target a larger fragment of SQL. Right, so what is this talk about? This talk is about extending NRC with grouping and aggregation, as simple as it is. And we expect, again, to have flat-typed terms in the extended calculus normalizing to a form that can be immediately interpreted in SQL, and hopefully also nested type terms, nested type queries that can be normalized and then shredded and finally compiled to SQL. And what do we need in this calculus? Well, at a minimum, we want grouping, partitioning a collection into key indexed subcollections, that is finite maps. Lookup, that is from a finite map, retrieve the subcollection matching a certain key. And group-wise aggregation, which applies an aggregate operation to each subcollection of a grouped collection. And this is the syntax of the extended calculus. The main change is that the type of collections has been replaced by a type of finite maps, where the index contains the grouping keys, a row of grouping keys, each with their attribute name. And when this row is empty, basically we have the original case of pure collections, because that means that there is only one empty grouping key, and thus only one subcollection. How do the terms of the calculus change? For starters, now singletons need to come with their domain, which is the key associated to the singleton. This expression here means that this is a finite map that associates to the grouping keys n the singleton m, and nothing, the empty set, to everything else. Unions are still the same, comprehensions are still the same. Then we add grouping that I have already shown you. Lookup, again, that was also in the introduction, as was the aggregation. I want to spend one word more on this other comprehension here, because while this comprehension, the original comprehension, only works on pure collections, not on finite maps, this is the kind of comprehension that we use on finite maps, and it's a comprehension that works on the key set. So given a finite map n, take all the keys from the finite map N, and for each of these keys, take the grand union of the M. Naturally, the main point of having a calculus like this is to have a rewrite system so that once we normalize away our terms, we get something that can be translated to SQL. And it turns out that the operations that we introduced in this calculus allow a rather simple extension of NRC. For example, when we have a key value pair and we want to look up a certain key, well, in that case, we will just return the value provided that the key matches the one that we have provided in the lookup operation. Grouping operations also have nice properties. Grouping over an empty map gives you an empty map. Grouping over a union map gives you the union of the maps. And here I want to spend a second saying that in this case, well, this union clearly is not the union of collections, it's the union of maps, in a certain sense of functions. So what does it mean? Does it mean the union of the graphs? No, not exactly. It means the point-wise union. Okay, so we are performing the union over the targets of the finite map, collapsing the collections that have the same key together. And we can also merge nested grouping by taking the disjoint union of the grouping keys. Okay? And the lookup operation has similar properties. The lookup over the empty map returns an empty collection, and the lookup over a union map returns the union of the lookup collections. The one case where we need a little bit of attention is when dealing with comprehension over a key set. That is this comprehension tagged here with the letter K. Clearly, comprehension where the generator is a singleton means that the only element we have to consider is that one key row in the singleton. So we just perform substitution over the head of the comprehension. And this comprehension operation is also distributive over unions of maps. So the comprehension with a union generator is the union of the comprehensions. This seems so far so good, right? But it could have been worse, because this is actually not the form of comprehension that I originally considered, because what you would normally want to have is that from a map, you retrieve key value pairs, right? Not just the keys. And in this case, we would substitute, when dealing with a singleton, we would substitute not just the key, but also the value. However, it turns out that that doesn't have good algebraic properties. In particular, if we used that form of comprehension as primitive, we couldn't have distributivity over union, because you remember that I told you union of maps is meant to be pointwise union, well, this is incompatible with the distributivity law. Does this mean that when we are in this situation, we are stuck? No, it means that we will use the comprehension just over the key set, and then the auxiliary lookup operation to deal with the values, and everything works fine. What do we have now? Now we only need to analyze normal forms and wish that the normal forms are simple enough to be converted to SQL. And you see, on the left column, you have the normal forms of flat queries in the original version of the calculus. And on the right, you have the normal forms on the extended calculus. And what are the changes? Well, the changes are that where there were singletons, you need to also consider the grouping keys. You need to consider two forms of comprehension generators, one for values, one for keys. You need to consider the operators that we have introduced, grouping, lookup, and aggregation, group-wise aggregation. But it's not so bad. It's still pretty rational, and it can guide an implementation. And the implementation works like this. So you remember, as I said at the beginning, NRC is more expressive than SQL because it has more expressive types. And for example, in this extended calculus, finite maps are a type that doesn't exist in SQL, but that is very benign because there is an isomorphism between finite maps and collections of key value pairs. So essentially, what we need to do to translate to SQL is to tag attributes in relations as keys or values. This is the case where we want to translate, this is the main case actually, where we want to translate a comprehension with a head that is a singleton with a key value pair. And that means that we can simply translate it to a select from statement as long as we tag the row 1 attributes, which are keys, as keys, and the row 2 attributes as values. For aggregation, we do something similar. This is where the group by statements come from. So if we are aggregating a finite map Q, we will need to group by the keys of the query Q while using Q as the input for the select, and return as the output the keys of Q and the aggregation. And this 2 over here, which was not in the original query, is the way we tag things as values. So to sum up, this was our initial goal, and what I have shown you is when you have flat typed NRC lambda gamma queries, you can normalize them and obtain normal forms that can be translated to SQL. But the paper also shows that when you're in the nested case, you actually can extend the shredding algorithm to work with finite maps as well, which is great. It was unexpected and a low-hanging fruit. There is another thing that I haven't mentioned. In this talk, I have discussed this calculus as if it had only one kind of collection, but actually in the paper, mixing set and bags is allowed, and there are some extra difficulties, but they are the same difficulties that you used to have in the version of the calculus with sets and bags, but without finite maps and aggregations. As I said, we translate to idiomatic SQL grouping queries, meaning that grouping is translated to grouping. It could have been translated with something else like correlated subqueries, but that would have had horrible performance. I haven't told you that the rewrite system is strongly normalizing, which is another nice property, because it means that you can choose the evaluation strategy that appears to be more efficient, and you know that you will always reach a normal form. And as I said, the full paper also extends to multiple collection kinds and to nested relational queries. Yes, to conclude, as far as I know, there have been other attempts at core calculi for grouping and aggregation, but this is, as far as I know, the only case in which you have several desirable properties: higher-order functions, finite maps as first-class values, and the possibility to deal with nested finite maps, and a full proof of strong normalization. And this is actually implemented at what you have seen in the talk is implemented in links. I wanted to say in the released version of links, but actually it wasn't released in time for PPDP, so you would need to get it from the GitHub repository. I mean, this is a good thing. In a commercial implementation, there are commercial implementations of language integrated query with grouping and aggregation, very used and very successful. But every now and then, a bug comes out because there is an imperfect understanding of the theory, and this is a step forward in a better understanding of the theory. And yes. In the paper, there are more details, and as for the implementation, what is not implemented yet is the shredding part, that is the part that deals with the nested relational queries, but the theory is sketched out in the paper, and it is rather simple. And this concludes the talk. Thank you very much.
So the obvious encoding is you could use is with just key value pairs, as you've shown repeatedly in here. So the benefits of this approach over simply doing that is that it's more efficient to compile into SQL grouping.
The benefit is that you don't lose the you don't lose in the compiled version the separation between keys and values, because once you use the isomorphism, it just becomes a collection. It's not a finite map anymore, and you can use that as part of an optimization process. And yes, if you have grouping performed in terms of group by operations rather than correlated subqueries, as you would end up doing if you just converted everything to key value pairs, that's usually considerably more efficient. And I can tell you that I had a development version that performed, that didn't use group by and performed everything just in terms of key value pairs, and it was horribly inefficient. I mean, in a certain sense, that's what finite maps do. Okay, the output of these finite maps is always a collection. So that multi-valued part of that is already included. Clearly, functions and finite maps in this calculus are rather different because finite maps are a glorified table by virtue of being finite, whereas functions don't have to be finite. So it's.
So this was also a question which I had. At the beginning, you also showed in the first version, you had also collections over any time. And therefore, I was also puzzled if you have functions. And you want
Yes.
a set of functions, you need equality on functions in order to have sets. So how does it
We
work?
do. Well, in the calculus, you have them. But when you want to translate to SQL, you will limit yourself to types that can be translated to SQL. So a collection of functions is not something that you are going to translate to SQL. But you use functions as intermediate steps in building queries. They are just normalized away by the right system before you send everything to SQL. And there is a complication with that when you deal with the case where you mix sets and bags, in part because deduplicating functions, like having a set of functions, as you were saying, you would need to have an equality between functions, and that is unspecified in the calculus how you would do it, right? So, I didn't tell you, but I hinted here. Here you see this TNC. That this was to say that yes, comprehensions have good rewrite rules, but there are a few cases when they don't. That is something that appears not really in this work, but in the previous work that mixes sets and bags. And again, the reason is related to the fact that you're not always able to normalize away functions in a collection when you mix sets and bags. So in order for that to work, you want not to have functions within sets. You can have them within bags, but not within sets.
Yeah, so thank you very much again, and all the speakers of this session.
Thank you.
just look. It's just a
Yes. Yeah, indeed. I mean, this just means.
Yes, but maybe so I will go to, that's why I wanted to try setting. Okay, where is this? I'm in settings here, print settings, system settings, display configuration. I think that I need to do that, right?
Oh yeah. But if
Okay.
if it's multi-valued, it's not finite. It's an infinite thing. It's like it can be an infinite set, which is. And I'm trying to do exactly this, integrate link into this language basically. And basically this is the problem now.
Right. In this case, in this language, all the cases where you have multiple values are finite. Right. Collections are finite.
So let me try another settings. Let me try again.
Just mute the mic. Sorry.
As functions, this is not what.
A new system, okay, you upload it into the system, they have people as in many publishers, and they take care of the paper. Thank you for attending
So
the
do you-
second session of PPDP today. Okay, I'm delighted to have Delia Kessner. We cannot see the screen. Okay. So we are delighted to have Delia Kessner from the Université Paris Cité. Okay, we're talking about that. Okay, but they changed the name.
Change of name.
Thank you. So she is our first invited speaker, the invited speaker today. Okay, I'm very happy to have Delia here. So she's a well-known researcher. Okay, in different calculus. Okay, and many other different topics. Okay, so I don't know. Thank you very much. Okay, for the invited talk, and I think that maybe we can start. So thank you.
Thank you. Thank you very much for the invitation. I'm happy to be here. So I'm going to talk about embedding call by name and call by value in a unifying framework. So it's like the continuation of the first talk in some sense. I'm happy that there was already an introduction to the topic. We want, in fact, to reason about quantitative properties of languages, and we are going to do that by using an embedding of call by name and call by value in a unifying framework. So when we talk about quantitative properties, here we have something specific in mind. We want to understand time evaluation, and we want also to understand the space or the size that a normal form takes. So of course you have other ways to understand space property, but here we will stay on this interpretation. Different models of computation, well, in fact, we will concentrate on call by name and call by value. A particular thing is that we want to capture call by name and call by value on open terms. So that means if you are interested in call by name and call by value, not only for functional programming, but also for proof assistance, then you need also to understand reduction and evaluation on open terms, because this is the things that are used inside proof assistance. And our unifying framework this time is not call by push value, but is a kind, a variant of bank calculus that we called distant bank calculus that I'm going to introduce. So, and I will use this. Yeah, but wait, okay. So I'm going to use these tags in order to, it's okay? Yeah, about the languages. So this picture that you will see this picture along my talk, this is summarizing what I'm going to present and what I would like to develop. And the idea is that by reasoning inside the unifying framework, which is the black one, this is a Swiss knife, we will be able to extract from the properties that we prove for the bank calculus similar properties for other models of computation. So this is a typical picture that you will see all along my talk. And when I'm talking about properties, there are, in fact, several kinds of properties. You have static properties. The static means you only look at terms. There are also dynamic properties. You look at reduction steps or reduction sequences. And also these properties may be qualitative or quantitative. And so we will detail a little bit what can we do with that by leveraging the knowledge we have about bank calculus to call by name and call by value. And others mean here it's like a wish in the sense that, as you probably know, call by need cannot embed in these unifying frameworks, at least from a clean point of view. But others mean that if you are able to encode other evaluation strategies in bank, then sometimes the techniques I'm going to present are general enough to be applied also to other models of computation than name and value. So this is the plan. I'm going first to, now it's working. Now this one, it's working here, but not on the screen. Okay. So first of all, I'm going to present the unifying framework, which is a distant bank calculus. Then we will discuss a little bit how untyped properties are captured in this unifying framework. Then we will go to the type word. And I will mention in particular an interesting result about the inhabitation problem. So let's start by the unifying framework. The unifying framework comes or is inspired from two different unifying frameworks. One is Levy's call-by-push value that was presented in the first talk, and the other one is Girard's linear logic. Both of them are unifying, but in fact they are philosophically different. In Levy's call-by-push value, you have a difference between values and computation, as it was mentioned this morning. So a value is, a computation does, and all the game is to go from values to computations in an explicit way, and from computations to values. Linear logic, in the linear logic, the philosophy is quite different. You want to distinguish in an explicit way which are the resources, the formulas of the logic, which can be erasable and duplicable. That means if you want to manage to duplicate some formula or some program, because programs and proofs are the same, then you need to say it in an explicit way by using some modality constructor, okay? So in principle, this is not exactly the same, but both frameworks are able to capture call by name and call by value in different ways with different encodings, but both are able to do that. And in 2016, Tomaira realized the gap or the common things between the two, and so he defined a calculus known as the bank calculus, which is the first bank calculus, which has then this nice property, bridges the gap between call-by-push value and linear logic, but it's incomplete. And what does it mean here, incomplete? I'm not even sure that incomplete is a good way, maybe non-adequate. The issue is that there are some open terms in particular that are denoting non-terminating programs, but in fact they are blocked, they are in normal form. So this is a paradox, because if you have a normal form cannot denote something which is non-terminating. So this is of course related to the semantics you give to the calculus, but the semantics is very reasonable and very natural, and the problem comes from the manipulation of open terms in call by value and in call by push value. So the same year, Erard and Guerreri defined a solution for that. In fact, the solution for this kind of incompleteness is already known, was already known, and it consists in adding commuting conversions. Commuting conversions are just permutations of redexes that make a block redex to be unblocked. And in this way, they recover completeness, but they lose confluence this time. So some years later, with Bucciarelli, Rios, and Viso, we defined what is called the bank calculus, the distant bank calculus, which is a bank calculus implementing reduction at the distance that I will explain later, which recovers completeness but also confluence. So this time, this is a calculus in contrast to different unifying frameworks that are defined as deterministic. So a calculus means here that you can implement in this calculus different strategies and different ways to reduce a given term. So confluence is important in this case. So let's see how the distant band calculus is defined. It is based on an extension of lambda calculus where you introduce, the band here is to denote values. So everything which is marked with a band, it is considered a value, and only those ones. In the sense here, variables are not values. And the reliction symbol modality is marked for the computations, and this annihilates the behavior of the band. And we use explicit substitutions, which appear also in the framework of this morning, which is just a constructor being able to implement commuting conversion, so being able to make the calculus complete. This is essential. So the operational semantics is defined by means of a reduction relation, which reduces everywhere except inside banks. And why you don't reduce inside banks? Because you consider that banks are values, and so you don't go inside values, like in call by value. You never go inside values. This is this is the reduction system which extends the one by error with explicit substitutions. This is not still sufficient, but this is the beginning. So you see here that you have three rules. One is firing a beta redex and creating an explicit substitution, like in calculi with explicit substitution. This is a typical rule in many different calculi for different purposes. Substitution is call by value substitution in the sense that you only fire your explicit substitution where the content is a value, and a value is a bang. So you can only fire substitution if you have a bang inside, and then you forget the fact that there was a bang, and so it's a different kind of substitution that is used in some call by push value frameworks. And then you have the rule that the annihilation rule, the reliction of bang of T is just T. Well, if you only use that, then you are not still complete. You need to add what is called distance. And distance, the idea is very simple and comes from linear logic. The idea is that when you want to communicate two terms, for example, in the beta rule, there is a function communicating with an argument. In the substitution rule, there is a bang communicating with an explicit substitution, etc. When you want to make this communication, you allow between the two subterms that are communicating a distance. And a distance means just a context of explicit substitutions, which can be considered as let constructors. So that means simply that the let definitions can be everywhere in the program. You don't care where the let definitions are. And so I will abbreviate a term affected by a list of explicit substitutions by using this notation. And at this point, the rules are converted to distant rules. And now you have a beta step, which is possible even if the abstraction is affected by a list of explicit substitutions, and then the argument comes later. Even in this situation, you are allowed now to perform a beta step. Yes?
So in the first rule, you play the... So the first rule, the redex, let's say, is in the, that is the T in your definition of LT, so that's the head term.
This one?
The head term. So it's in front of all substitutions.
So L, you're talking about this rule?
Yes, so L, because you
Here?
specify L as saying it is a T with a series of substitutions.
Yes.
So that particular L says there is one term and then there are substitutions.
Yes, here the L is pushed outside. So L was affecting only lambda xt, and L is pushed outside. Of course, all this is modulo alpha conversion, so you only do that if there is no capture of variables.
So the substitution that you create gets put at the end?
the substitution that you create, let's see an example, okay? So the substitution that you create is the inner one. Let's see an example. Take the identity. So this one is the distance between my abstraction and my argument, right? And when the step is performed, the distant context is pushed outside. Okay? Again, you need to be sure that there is no capture of variables, but you can use alpha conversion as is usually done. So this is an example of dB. D is for distance, and B is for the starting beta redex. Then you can substitute, for example, this redex because there is a bang, but Y is not in X, so you lose the information. This is an erasing step. Now again, you have a bang, so you can fire again a substitution, and you obtain this redex, and now the reliction of bang is just the identity, and you finish. So this is the typical way in which you reduce in the distant bang calculus. Well, distant calculi were not defined for the bang calculus, but in principle for many different kind of calculi, and in particular for lambda calculus. And this was joint work with Beniamino Acatoli, and this is inspired from linear logic, because in linear logic, and in particular in proof nets, the connections between the nodes of your proof nets are done even if you have in the middle a lot of definitions and other cats, and the cats of the proof nets are the explicit substitutions of the calculus, okay? So this comes from there. Well, now you have a language which is complete in the sense that you don't have anymore the strange phenomenon that I mentioned before. I have an example at the end if you are interested in more details. The system is confluent because in principle it's not deterministic. And it's even better than confluent, it is diamond. Diamond means that if from one term you can diverge in one step to two different terms, then you can converge also in one step. And this is very interesting because diamond calculi are in fact deterministic in some sense because all evaluation sequences have the same length. So if you want to study quantitative properties of evaluation, diamond languages I mean, you can have the freedom to enlarge your calculus to a one which is non-deterministic, but keeping this diamond property. Well, and the fact that it is inspired from linear logic has some advantages when you want to export some ideas and some techniques coming from linear logic. So this is the language that we are calling our unifying framework. So let's see how we can capture now properties, and in particular reduction of call by name and call by value. So I'm not presenting in detail our formulation of call by name and call by value, but just to give an idea, well, I think this is the kind of things that you know very well. In call by name, and we are allowed to reason about open reduction, but in call by name this is not a problem. Any term can be passed as an actual argument. And this is important because this idea is the one applied to encode call by name in the bang calculus. So here is an example. You have an argument here, and you don't need to reduce the argument in order to pass the argument to the function. In call by value, you can only pass values as actual arguments. So in the same example, you first need to evaluate the argument. This gives 9, and then you can continue your evaluation. And again, this is crucial when you are going to encode call by value into the bang calculus, because since only values can be passed as actual arguments, that means that only values can be duplicated and erased by thinking to the philosophy of Girard. And in call by name, since any term can be passed as an actual argument, that means that any term is potentially erasable and duplicable, okay? Well, So now we want to fix and to understand which are the good encodings for call by name and call by value. But before entering into the detail of the encodings, let's see what we expect from these encodings. And what we expect is that if we have a property in call by name on a term t, then we would like to have the same property in the bank calculus for the encoding of t with respect to the call by name encoding, and the same for call by value, and vice versa also, in the sense that we want an if-only if here. We want to have a good correspondence between call by name and the encoding of terms in the bank calculus. So we keep in mind that because you are going to see this kind of scheme on the rest of the talk. Again, when we talk about properties, we can think about a static property. Static here means we are going to compare term t with respect to the encoding of t, either in call by name, both in call by name and call by value. And a dynamic property means here that we want to compare a reduction sequence in call by name with respect to the encoded reduction sequence in the bank calculus. So we want both of them to be okay. Are there any questions or?
So static means without evaluation of the semantical?
Static means that we don't look at the reduction semantics. Yes, we only look at the term. A static one. Well, I'm going to show some examples, but can be related to an untyped property, which is static, or a type property, which is also static, right? And the other ones are well, I'm coming. So let's start with what is known as Girard translations. So Girard translation is translations in the framework of linear logic, right? So the call by name encoding of Girard is given by this definition here. What, if you recall my slogan, every term can be passed as an actual argument. That means that when you have an argument, what is an argument? An argument is the right-hand side of an application or the content or of a substitution. So since any argument can be passed as, can be erasable and duplicable, then that means that in these two cases, you need to put the modality bank in order to ensure that these arguments are potentially duplicable, okay? So this is quite a simple idea in the encoding. Call by value, it's a little bit different. In call by value, you say, well, any value, and in call by value, a value is a variable or an abstraction, not in the bank calculus, but in call by value, in Plotkin call by value. So you need to encode values, variables, and abstractions with banks. By these two lines are saying that, well, any value can be duplicable in the bank calculus. But the problem is that if you put a bank in the values and in particular in the abstractions, then when you want to use these abstractions in nonlinear positions, that is in the left-hand side of applications, then you will have a bank applied to a bank, which has no meaning because terms and programs in linear positions are not duplicable. So in order to annihilate this effect, you put a dereliction on the left-hand side of an application. This is the idea of Girard encoding of call by value. Let's see the properties here. So we have still, well, here I'm using the reflexive transitive closure, but this applies for one step also. So the dynamic property, as the dynamic property, I'm starting with these ones because are the ones that are well behaved in call by value in particular. In call by name, everything is okay. So reduction in call by name translates to reduction in the bank calculus of the encoded terms, and the opposite also holds. So that's fine. This translation is okay. For call by value, things are more complex, and you can only translate from call by value to bank, but not the other way. And that's why, why is that? Well, this is because the bank here is only indicating the possibility of duplicated term, but not the possibility of forbidding some position of the term for reduction, okay? So in call by value, you can never go inside an abstraction, so you can never go inside a value, but in the bank calculus, you can go inside an abstraction, even if you cannot go inside a bank. And here there is a mismatch, and that's why you have this problem. For the static property, it's a little, it's even worse. If you have a name normal form, that means a term which is in normal form for call by name, then the translation of this term is a normal form in the bank calculus, and the opposite also holds. But for call by value, you don't even have translation of from normal forms to normal form. And this is an example. When you have x applied to y in call by value, this is a normal form. But in call by in the bank calculus, this is translated by a dereliction coming from this line and a bank coming from this line. And so at the end, you have a redex, which is a redex which is called an administrative redex, but is a redex anyway, and this is also the thing that you wanted to avoid. So I'm telling that there are two different approaches to eliminate these kind of things, but at the end you don't have a good correspondence. So what we are going to do is to modify the call. So this was done with Bucciarelli, Rios, and Viso, to modify the call by value translation by using what is called in rewriting a super development. So the idea is that when you are translating an application, you look at the left-hand side, and if there is a bank, then you don't want to put a dereliction on the left, and so you perform the administrative step on the fly. And in this way, you don't change the notion of substitution, but you avoid the there bank administrative step. And so at this point, you obtain also a good static, you are happy with your preservation of static properties because a value normal form is translated to a bank normal form, and the opposite also holds. But you still have this property here, which is not perfect in the sense that you can go from value to bank, but not the opposite. So at this point, you can change again the translation. I will not enter into the details, but the new translation is this one. This is recent work with Arial and Guerreri. And just the idea behind this, which allows to obtain an if and only if here, is that in the translation of an abstraction, you are using now two banks. The first one is used to say that this is a value and can be duplicated. The second one is used to say it is forbidden to go inside. This is something where it is forbidden to go inside. And this is also something that gives an idea that the bank here in this unifying approach, it has two roles. One is to duplicate terms, and another one is to forbid reduction inside some terms. But at the end, we have what we want, and we are happy. And then I will tell now which kind of result you can obtain with this kind of encoding. Some of them were obtained with the second one, which is not well behaved always, but already it is good to obtain many different results, and others were obtained with this third option. So let's discuss about the untyped behavior of the encodings. Again, I would like to derive a property for name and value by using the property for bank. So again, my picture. And we recently used that. This was used with the third encoding for a property called factorization. So factorization is a well-known property in rewriting theory. It is technical to be defined in a formal way, but just to give an informal idea, the idea of factorization is that giving any reduction sequence in any reduction relation, you say that it is possible to factorize it if you can rearrange the steps in such a way that the first steps are the relevant ones. The relevant ones are also called external, usually in rewriting theory. And at the end, you perform all the steps that are not very important, that are irrelevant, and that are maybe can be even ignoring an implementation of a language. So this is informal, I know, but this is just to give you an idea. So what we did is we first showed that the bank calculus admits factorization, and the idea of external reduction here is the one that never goes inside the bank, and the internal one is the one that goes inside banks. And from that, we derive factorization for call by name and call by value by just using our preservation properties of the previous slide. Okay, so this is the kind of property that you can show. And now let's talk about quantitativity, or about quantitative properties. So we come again to quantitativity, and quantitativity is time and space. So the idea here is, can we derive evaluation time for call by name and call by value by just using our preservation properties and the fact that we know which is the evaluation time for bank? This is the kind of question that we want to answer. The same for space. Can we derive an information about the space or the size of the normal forms in call by name and call by value by just using the information that we have for the size of normal forms in the bank calculus? Again, this is the kind of picture that is illustrating what we are trying to do. So in order to do that, we are not going to reason in an untyped framework, because usually this is very complicated, and even I don't know if it is possible to do that by using only syntactical tools. So we move to typing systems, so they are called typing systems, quantitative typing systems, but in fact they are undecidable. So maybe, I mean, people from the programming community are shocked when they see that these are called typing systems, because they are not decidable, but we like to call them typing systems. And in fact, they are models, in particular relational models and quantitative relational models, the ones that I'm going to use. And they are very useful to reason about these kind of things. So let's go to the type part, and let's try to understand how we can encapsulate quantitative properties of call by name and call by value. To start, briefly to present intersection types, these quantitative type systems are intersection type systems. So to present them, I would like just to mention a property, typical property that is verified by simple type systems, the ones that we usually know and manipulate in functional languages. Well, of course, maybe, I mean, there is no polymorphism here. I'm just talking about a very basic typing system. So usually when you have a simple type system, you can show that typability implies normalization, termination. For example, if we are in the framework of the lambda calculus, it is sufficient to have a narrow type and no more than that. And of course, you are leaving some terms outside. Typically, lambda x applied to x is a terminating term. It's in particular a normal form, so you cannot reduce anything from this term, but it's not typable. And it's not typable because the x here is playing a double role. On the left part of the term, it is a function, and on the right-hand side, it is an argument. And so you cannot assign a double role to a variable in a simply typed term. So what intersection types try to do is to enlarge the yellow part, that means the set of typable terms, going through the green part. And in particular, you are able to capture all the terminating terms. So when you have a good intersection type system, you have a characterization of termination in the sense that a term is typable if and only if it is terminating. So for that, it is sufficient to add an intersection constructor. And this term that was green before becomes yellow because now lambda x applied to x is typable and terminating, both of them. And the intuition now is that x, which has a double role, has also a double type or an intersection type. So on one hand, this x has a functional type, and on the other hand, I mean the occurrence on the right, has the type which is in the domain of this function. And so you can capture these kind of things. Well, you see here that these systems cannot be decidable because they are characterized in termination. But we are going to use them in order to infer some properties. And so now I come back to the history of these intersection types. And just I'm not going to give a list of the history of the development of these intersection types. The list is very, very long. But just to mention that there are two ways to deal with intersection. Either like it was created in the 80s by Coppo and Dezzani, the Torino school, it's idempotent, or you impose non-idempotency. And so non-idempotency, why this is inherited from Girard's linear logic, because the tensor constructor in linear logic is non-idempotent, and the intersection can be seen as the tensor constructor in linear logic. So the first non-idempotent systems that at least I'm aware of come from Gardner and Khoury, and the theory was developed a lot these last 10 years. So on the left you have, well, on the left and on the right, the intersection is associative and commutative, but on the left is idempotent and on the right is non-idempotent. And so with these axioms, if you want to keep some intuition, idempotent intersection types are sets. So you cannot have repetitions of types in your sets, but on the right you have multisets. And this gives already an idea of why, on one side, we only can deal and show qualitative properties, and on the other side, we can also reason about quantitativity. Because in a set, you don't count, I mean, you don't care about, because you have forget about the number of occurrences of an element in a set. I mean, you suppose that there is one, but maybe there are more than one, and you don't want to see that in the structure that you have choose to specify that. And so the kind of property is a term is typable if and only if it has this property. So you can say yes or no, nothing more. On the side of non-idempotent types, you can show that a type term has a property if and only if, but also you can add some quantitative information. I will show in detail, and we will discuss how to do that. And so that's a very important point. Okay? So let's go to a concrete example of quantitative typing system. I'm using this grammar of types. So you see that you have base types and you have multisets of types. And the multisets are used in particular on the left side of the arrows. And they will denote multiplicity or potentiality for the duplication of terms. The judgments are going to be of this form. So in this kind of systems, you type a term with a type, but the variables have all multisets of types because the variables are the ones that can be erased and duplicated. So if you have an empty multiset, that means that you can only erase the variable. If you have a multiset with one element, that means that you can only linearly substitute this variable. And if you have a multiset with more than one element, that means that you can really duplicate the variable. It's really duplicating what is receiving with, by means of substitution. So the system B is a one defined in 2020. It is inspired from Gardner and De Carvalho. So you have typical rules for abstraction and application. In particular, for application, you have a multiplicative rule. That means that the hypothesis that you use for T and the hypothesis that you use for U are collected using multiset union. And so that's why you are collecting all the information in a quantitative way. The axiom is relevant in the sense there is no weakening in this system. The rule for explicit substitution is just derived from the other one, so it's not very interesting. And then for the bang, you have to collect, because the bang is saying that this term is going to be duplicated, then from a typing point of view, you need to collect all the typing information that you have for T. And the dereliction is doing the opposite, but can only be done where a term can only has only one information. So you see also in this slide that to type a value, you come for the typing of the computations, and to type a computation, you come from the typing of a value. The notation I'm going to use for derivation in this system is this one. So this means that T is typed with sigma by using the hypothesis of gamma in the type system B, and this is the name of the derivation. And the name of the derivation is important because we are going to use information in the derivation in order to reason about quantitativity. So here is an example. In this example, we are typing this term without hypothesis. The argument is a bang, and you see that to type a bang, we need two different informations, but because we have two different types. So one is obtained in this subproof, and the other one in the, on the right-hand side. And the abstraction is performed in a classical way, and the bang X is, the bang rule is also used here to type bang X, okay? So nothing very difficult. The important thing is that now you have multisets. Well, so let's recapitulate which is the kind of thing that you can show in idempotent intersection types. So in idempotent intersection types, you can show that a term is typable if and only if it is terminating. So if you take system B and you forget multisets and you replace the multiset with sets, this is the only kind of property that you will be able to show. So when you go from typing to termination, this is called soundness, and when you go from termination to typing, this is called completeness. Now in system B, you can show more than that. You can show that a term is typable if and only if you have termination in bang, but also if termination occurs in time t and the normal form is of space S, then you can show that the sum of the two is bound by the size of the proof, the number of nodes of the proof that you are using to type the term. So that means that you collect quantitative information by looking at the proof. The proof is in principle static, okay? And the information that you are collecting is information coming from a dynamics of the calculus. And so this is the kind of improvement that you can have when using this kind of systems. We will see that it can be improved a little bit more, but for the moment we have that. And so already you can say that system B is qualitatively and quantitatively sound and complete for the band calculus. Okay. So just a remark for those that are not used to this kind of system is that when you usually show soundness, that means a typical proof in our community showing typability implies normalization, usually you need two ingredients. One is substrate reduction, okay, saying that if a term is typable and it reduces, then the reduct is typable. And the other one is some kind of reducibility argument. So there are some special cases where you can avoid reducibility arguments, but in general, you need the reducibility argument. Here in this framework, you use a more precise property of substrate reduction, which is called quantitative substrate reduction, that I will describe. And then you don't need any more reducibility arguments to show that typing implies normalization. You only observe that there is a decreasing measure, and so the proof of typing imply termination is trivial. And quantitative substrate reduction usually reads like that. If you have, and this is in particular true in system B, if you have a typing for your term t and you reduce t to u, then you can type u, and the proof, if you compare the size, here I forgot size, if you compare the size, the number of nodes of p with respect to the one of p prime, there is a strict relation between the two. And so now if you have a type term, then it is trivial that it is strongly normalizing, because each time that you perform a reduction step, there is something which is decreasing. And these measures are integers, just integers. So at the end, you know that it is normalizing. A type term, it's trivially normalizing. So this.
The idea is that since it's a multi-set with the variables, you are consuming one of the variables. So, more or less.
Yeah, in fact, it is a little bit more complex than that, okay. But we can come back to that. The idea is that in this kind of system, you anticipate all the copies that you are going to perform during reduction with the multisets. Okay. So you are not only reducing the multisets, but you are also reducing some subtrees of the typing proof. Okay. Okay. So this is just a remark, and now let's come back to name, value, and bang. So there are typing systems for call by name and call by value. The one for call by name, well, I put here the Carvalho, but it is Garner and then the Carvalho. I'm sorry for that. And for call by value, there are different variants, but here we take the one we defined with Bucciarelli, Viso, and Rios. And what it can be shown, and this is not difficult at all, is that a term is typable in call by name or call by value if and only if the encoding is typable in bang. And this is interesting because
since these typing systems are powerful and capture termination, then you can say different things. For example, first corollary is that soundness for name and value can be derived from soundness for the bank evaluation. This is the first corollary that we have. But more generally, well, both systems are sound and complete, both. There is a repetition of 4. And as a corollary of that, termination of call by name and call by value is related to termination in the bank calculus for the encoding. So this corollary is just taking the form of my general scheme of expected results and instantiating that for the property terminates, okay? And so, in particular, upper bounds for name and value relate back and forth to upper bounds for the bank evaluation. So, without entering into the details. Now the question is if we can do a little bit better than that, because upper bounds are nice, but are not optimal. I mean, upper bounds can be very, very big. And so for that, I will try to explain this part as clear as possible. I hope to arrive to explain that. So as we discussed, upper bound means here that by taking the size of a type derivation, we obtain an upper bound for the time and the space of an evaluation. This is the best we can do with the kind of system that I showed before, for example, with system B. The problem is now that time and space do not behave in the same way. In particular, space can be exponentially bigger than time. This is known as the size explosion problem. So in particular, there are terms that are, let's say, with size n, which reduce in time n, or O of n, to something which is exponentially bigger. So that means that if we have an upper bound for the sum of the two, we are not really giving good information about time in particular, okay? So there is another way to do quantitative reasoning by means of quantitative types, and in which you split time and space and you reason in an independent way. So your typing system now is giving information for time and information for space. Okay, so at the end, of course, all that will be encoded in the size of the proof, but you will be able to distinguish which information applies for time and which information applies for space. And to do that, that means that we don't have just one way to measure. On the left-hand side, it was just the number of nodes of the tree. You will need to be more fine than that, and you need to split the counting in different ways. To do that, we will use judgments that have counters. So now a term is typed with a type sigma using a set of hypotheses, and also with two integer information, one called t, because it is supposed to give the time information, and one called s, which is supposed to give the space information. And so this was done for the lambda calculus with Acatoli and Lagrange some years ago, but it can be also adapted to different frameworks, and in particular to the bank calculus, okay? And so without entering into the details, I will not show you the rules of the system, but what is a general scheme of a typing rule in such kind of system is something where you have counters on the premises, and you have a counter in the conclusion, and the counters in the conclusion are computed by using some function on the counters of the premises, okay? So all the rules have this form, and at the end you have a system where there are counters for every derivation. So you can do that for the bank calculus, for call by name and for call by value. I'm putting the name E for exact, so the system B can be refined to an exact type system called EB, and the same for call by name and the same for call by value. And you can now pass from this one, which was the previous one, the kind of property that we are able to show with upper bounds, which just give an information which is not very satisfactory, to something now which has this form. So a term is typable with a type and a set of hypotheses and with two counters if and only if the term terminates using T steps and the result is S. Okay? So now you also extract information from the typing derivation, but now you have exact information. Okay? And you can do the same for name, and you can do the same for value. And in particular, you can also show that the counters that you use for call by name are related to the counters that you use for the encoding of the term in the bank calculus. And in particular, look at the counters, they remain the same. So that means that evaluating in call by name and evaluating in the bank calculus have exactly the same cost, right? Exactly the same cost. For call by value is different. The time is not equal because you have these dereliction banks, administrative work that you need to consider. And so you show that the space is the same, but the time is not the same. And you have here, I'm not showing the details in this talk, but you can show which is the exact relation between T on the value side and T prime on the bank side. So you know exactly which is the delta which is lacking in the bank side in order to evaluate one term on one side or the other one. Okay, so we can say as a corollary that time and space for name and value evaluation relate back and forth to time and space for bank evaluation. Again, we have the same kind of picture that we showed before. Now we will discuss a little bit inhabitation. It's less technical. At least I will not enter into the technical details. So in order to introduce inhabitation, I'd like to start with typing. So what is the typing problem? The typing problem is usually you fix a term and you want to find a type and a set of declarations for your variables that are in the hypothesis in order to have a typing derivation. So when you have the typing problem, you have a term language for your term, and you have a typing system for your type information. In the inhabitation problem, it's the dual one. You fix gamma and sigma, so you fix the typing information, and you are looking for the term. So again, you have a typing system. This one is the one that is fixed as the input of the problem, and you want as the output a term, a program which belongs to the term language. So I will discuss about this inhabitation problem. And what is interesting is that the inhabitation problem in type theories is called inhabitation, but in logic is called proof search, and in programming is called program synthesis. Well, it's a special kind of program synthesis, because the idea, well, proof search is clear because proofs and terms are the same, so this is natural and intuitive. But program synthesis is just if you look at gamma and sigma as specifications, then looking for a term that verifies this specification is a kind of program synthesis, not very powerful as the things that we now see that are done in program synthesis, but it's already a kind of program synthesis. Okay. So let's go to the case of lambda calculus. In lambda calculus, typing, if you take simple types, then everything is nice and is, of course, decidable. As I mentioned before, For intersection types, both idempotent and non-idempotent, typing is undecidable because a term is typable if and only if it's terminating, so it cannot be decidable, okay? Because we know that termination is undecidable. So now let's go to inhabitation. In the case of simple types, again, everything is nice, so it's decidable. But in the case of idempotent types, inhabitation is undecidable. This was shown by Ursiching a long time ago. And what is interesting and surprising, but at the end not even very surprising, I will try to give you some intuitions, is that in call by name for lambda calculus, inhabitation is decidable. Okay? So this was joint work with Bucciarelli and De La Rocca.
This is the call by name time Simon system.
For the call by name system, yes.
Yeah, yeah. So this is not the intersection type system with non-idempotent types. This is in a type assignment system where you encode call by name.
This is the quantitative, the non-idempotent type system by Gardner, yes, for call by name.
Okay.
Yes. So, of course, the question now is, and what about call by value, and what about others? I mean, but you can imagine that the idea will be more or less the same. And the reason why this is decidable, why in idempotent types is not decidable, comes from this slide. So when you have idempotency, that means that you don't count. When you say that sigma intersection sigma is sigma, that means that 1 plus 1 is 1. So you are not really counting. You don't care about the quantitative structure of your intersection type. When you are in the non-idempotent world, 1 plus 1 is 2. And so you are counting, and if you can count, you can bound. And that's the reason, and that's the intuition why in the idempotent world, your search during the inhabitation problem is on infinite resources, because you can always suppose or suppose that there is one more sigma which is hidden in your intersection, while in the non-idempotent world, you are looking on finite resources. So when the resources are over, you cannot go anymore for any search, and you are done. Okay? So this is a kind of intuition. So now, which is the goal? Well, of course, the goal at the beginning, well, to fill the table and to understand, well, we know already that call by name is decidable, but the goal before that was to understanding if in this framework, call by name and call by value have inhabitation problems that are decidable. This is a first goal. And this corresponds just to identify the red Swiss knife and the green one, nothing more. A second goal, more ambitious, is, well, let's first understand if there is decidability for Bang, and if it is true, then let's prove decidability for name and value from the decidability of Bang. So this is the picture that you have already seen during the talk. And a more ambitious goal is, well, let's not only stay about decidability, but let's try to find all the inhabitants that we can, that are justifying the fact that the problem is, the input has some inhabitant, some answer. And in particular, we want to do that in a general way, in order to maybe in the future, if you have interesting other models of computations, then you don't need to redo all the proofs again. You have already the tools and the things that are ready to say, well, also in other models of computation, this is true. So the methodology is based on two things. So first of all, instead of just one solution for the inhabitation problem, the solution here is in red, we want to compute all of them. So this is already the way to go from just deciding decidability to finding all the inhabitants. But the problem is that this set of solution is usually infinite, so this is a problem. And in order to do that, what we do is to define what we call a finite generator set, which is covering all the possible answers. And this set is finite and also sound complete, in the sense that you need to show that this set is sufficient in order to cover all the cases. So at this point, your algorithm will not answer an infinite set of terms, but it will give you a finite set which is representing all the possible answers. So I don't want to make you scared. The algorithm looks like that, and I will not discuss it in detail. But some observations about the algorithm. So first of all, it's an inductive algorithm given by inference rules. So in the conclusion, you have, on the right-hand side, you have different kind of calls. So there are calls of the form H, call of the form N, etc. And on the left-hand side, you have the answer that is given, that is built at the end of the call. In the premise, you have the recursive calls on the right-hand side, and on the left-hand side, you have some conditions that need to be verified in order to make the recursive call, okay? And an important issue which is crucial here in order to be as general as possible is that the rules are parametricized with respect to a symbol G, which is a symbol of a grammar, and this grammar is just giving the form of the normal forms or the terms that are in your finite set of generators, okay? So these are the key ingredients of the algorithm. I'm not going to enter into details here. Of course, the algorithm is non-deterministic in the sense that at one point you can apply more than one rule. This is typical in some specifications of inhabitation problems. But it is possible to show that the algorithm terminates. So this is just done with the measure. The measure is not trivial, but it's quite reasonable at the end. And we can show that it is sound in the sense that if your algorithm computes a set, then everything that you find inside your set is typable, so that means it's an inhabitant of your input. And it is also complete in the fact that if you know that there is some term for your input, then you will find some term which is related to T with the original T by using this generation of that I mentioned before. And the algorithm was implemented by Victor Arial in OCaml. Okay. So now how we can apply this to infer inhabitation in call by name and call by value. So I will show some very reduce and simplify ideas, but the issue is that you start from a grammar for lambda terms, and you need to know which is a grammar for normal forms in your language. Then you encode this grammar in the Bang calculus, in the Bang word, so you have the image of the encoding, and your algorithm is run on this image. At the end, you have a set of answers, and these answers are decoded to the name word. And this is possible because you have the possibility to encode and decode from name to Bang and from Bang to name. And so at the end, you have the result of your name inhabitation problem. And the same can be done for call by value, and if you have another model of computation, you will be able to do the same. You encode into Bang, you perform the inhabitation, you run your inhabitation problem on the Bang side, and then at the end, you have the result just by applying the decoding. Okay. So in your table, in this table that I showed before, we can now say that it is decidable by completing this in this way. It is worth noticing that there are intermediate systems between idempotent types and non-idempotent types. This was, for example, explored by Yakov Rehov. When you have idempotent types, but with some restriction. For example, you look at a given rank, for example, and in this way you can also recover decidability. Here you don't have a restriction at all on the kind of types that you have in your problem, but the types are quantitative. So it's another kind of question that you are answering when doing this. Well, so it's time to conclude. Just to make a summary of the talk. So I presented the unifying and type framework. There are no types in this distant bank calculus that I presented. This untyped framework is able to capture call by name and call by value also in their untyped versions. We showed some typed extensions by using non-idempotent types, and in particular, two of them, type extensions using non-idempotent types are able to capture upper bounds on one side, and also type extensions where you can capture exact measures for time and space of bank, and so also deriving these properties for name and value. And a unifying algorithm on the bank side, which is also able to capture the navigation problem for name, value, and other languages. There are a lot of questions and also some interesting ongoing works. I wanted just to mention here the ones that I consider interesting. So you see here classical control operators. So it was in some sense covered by the first talk. What we are trying now to do is to approach and to study some interesting properties of calculi like approximation, solvability, genericity, etc., that are difficult to be understood for call by value. So as you know, in call by name, everything is perfect, and when you reason with call by name lambda calculus, usually everything is nice. When you want to reason with call by value, you don't have these easy tools, these easy properties, and I think one of the problems is that in Plotkin's call by value, you are mixing two roles for the abstractions, because the abstractions are values and are also computations in some sense. And so that's a problem to reason in a proper way with call by value. By going to the bank calculus, where the things are distinguished in a proper way, also values are bank terms and you don't mix with the functions, for example, it is possible to have a more clean answer to many difficult problems actually in the literature. For one of them is solvability, for example, which is not a trivial problem. And so we are now concentrating on this part. And another thing is that if you want your bank calculus to be like a more real programming language, having interesting features of, for example, pattern matching, effectful computation, etc., this in some cases is not trivial. So we are trying also to do that by keeping an eye always on the translations to call by name and call by value, and knowing that in some particular cases, even effectful computation, for example, is not trivial in the call by value setting. Okay, so we are trying to relate all these things in a unifying way. And that's all. Thanks for your attention.
Questions?
Okay, I enjoyed that, I have to confess. So my main question is that so I understand why you use the bank calculus, because of its origin and its definability, etc. So having studied it myself, the thing that bothers me is that it is, apart from the redax, which says that you can only contract if you have a value as the operand, you are allowed to run the operands. So you can do the evaluation of the right-hand side in an application so that it becomes a value and then you do the contraction. So call by value is inherent in the bank calculus. Yeah. So I like the call by push value calculus because it doesn't do that. It very strictly limits. It says no, you can't ever run the right-hand side. So I'm very curious. Do you think that these results that you have, could you achieve them in the context of the call by push value calculus?
Precisely, I don't think so, because here a crucial point is that when you interpret call by name, you are using this idea that every term can be duplicated, so every term becomes a value in the bank calculus, and this is crucial. So I don't think so. I think that all these results that we have is precisely because we are making a very, we are taking the notion of value as a very important and primitive notion in the bank calculus. You can only substitute bank terms. If you want to capture call by name, you can just by saying, well, every term is banked, like in our translation. But I don't see how to manage if you want to avoid that.
Okay.
But we can discuss later, because I mean it's interesting. There are a lot of options, and sometimes they are related in the sense the kind of substitution that you use, for example, in your case, is related to your encoding, and the same in the bank calculus. The same, we are using only substitution on bank terms, and this is related to the kind of translation that needs to be used.
So thank you, Delia. Okay, so it was a very nice talk. Okay, so I have more than questions that we can also talk later. Okay, I was, you know that I work on rewriting logic mod. Okay, so I was very curious that in habitation, if you can you go back just a moment? Yeah. So when you have the first slide, talking about all the terms returned.
This one?
This one, yeah. So I was very curious because, so you see that in mod, there has been many approaches of encoding different logics, some formalism, some models of computation in mod, okay? There's a long story about that, okay? But narrowing and unification in mod is kind of a new thing, okay? And then I was really funny because so that question there, okay, is just asking that if you put a variable in the place of the t, okay, which are the substitutions to that variable, okay, that made the whole statement true, okay? So it happened that this inhabitation in reality is like a unification query, okay, if you had this bank calculus encoded into mod, okay? So it's just, as I said, so it's not really a question. It was just a comment that I found that very interesting, because also in the next slide, when you have the slide, all the inference rules, some of them are really substitutions. Okay. In reality, when you say that G goes to derivation of G prime, okay, in reality you are constructing a substitution, and usually
this is a rule of a grammar.
Yes, but that rule of a grammar can be seen as a substitution, and it can be done automatically by unification. Okay, so I was curious that what you have here, so encoding inference rules in mod is something that many people have done. Okay, but then the idea is that now that we have I'm sorry, because it's like I'm selling myself.
Yeah. No.
The idea that since now we have unification in mod, then all those steps will be performed by unification automatically, okay? And in reality, what you can get as a substitution will be these grammars that you are looking for here. So
Okay, but I'm not sure that you want unification everywhere in this algorithm. So maybe for the grammar it could be interesting, but I'm not sure that you want unification in every sub program of this program.
Yes, but because I mean, it depends where you put a logical variable.
Yeah. Okay.
So if you put a logical variable here, then I'm asking for which possible substitutions to this logical variable do I get this?
Okay.
And then depending on where you put the logical variable, you can obtain one thing or another.
So in fact, you are suggesting that we can implement this algorithm in
mod?
Mod very easily, if I understand well.
Yes,
this was implemented in OCaml, so you need to backtrack sometimes because you go for you progress in a path, and at the end you realize that there is no inhabitant in this path, and so you need to cut this path from the tree, and you backtrack. So yes, of course, this is typically captured by a logical framework. Yeah.
So that
interesting.
was my comment only.
Okay. So interesting.
I just want to take the position of defending intersection types as they were defined. So the original research papers, I think 4 or 5 of them before the Barres-Kopitizzani paper, were focusing on normalization and not termination. Termination is strong normalization. So when I stepped in, I did the strong normalization proof first. So the systems are defined more with an eye on semantics than any kind of analysis. So that's why the intersection of two types is the type itself, because you see a type as the set of all terms having that type. And so if you would define semantics of non-idempotent intersection type systems, you would end up with the same models as the original. Okay.
But they are related, and this was studied by
Okay.
So the non-idempotent types are just a refinement of the models that you are using.
Okay.
Well, we still have time. Just a very little comment also. Idempotency, I'm sorry, for what I got to say, but idempotency is also something that we do a lot in mod. Okay.
Yes.
So even if idempotency, it is true that it has infinite equivalent classes. Okay. We do have lots of methods in mod for solving problems. I mean, it is used a lot because it's necessary for sets. Okay. And this question, okay, of whether you are reasoning in an infinite equivalent class, okay, at the end in mod is kind of irrelevant. It's very simple, okay, because the idea is that you have implicit the idea of normalization. So when you have plus 1 is reduced to 1, okay, but you ensure that any possible rule is doing like the backwards, but locally, okay. So I was also curious that it seems to be a big problem in the potency. Okay, but it is not in mod. So
no, it's not a big problem. Well, it's just a problem if you want quantitative properties.
Okay.
Just, but it's not a problem at all. Yeah. So in particular, the issue is that in this table that I'm showing, you see that it's a problem because, well, if you are idempotent, inhabitation is undecidable. So it's...
but the idea, for instance, if you think in terms of unification, as I said before, then the idea is that you may have 2 unifiers, so 2 solutions, which will be two inhabitants of that thing, okay? And the idea is that one normalizes into the other. And then you can claim that those solutions, as the result of doing equational unification, you may have an infinite number of unifiers, of solutions, okay? But you just keep the ones that are normalized with respect to, I mean, it's an
you can relate the two, you mean?
Yeah,
yes, of course. No, that's true. This is just a refinement. So you don't replace one by the other one. You just refine the first into the other one when you want to be quantitative.
So there is the idea that in mod you have associativity, commutativity, idempotency, so we have many of these, and it's just a question of handle them in the right way. So. Oh.
I was reminded of one question I had on your slides. You, at a certain point, you talk about the measurement of the call by value and the call by name systems with respect to the bang, and then you say that there exists a function that you didn't specify from the call by value measurement to the bang measurement. Yes. Can you go back to that slide, please?
This one.
No, you had a slide where you actually you had written an F and a G.
Ah, no, but this is not related to call by name and call by value. This is this one.
No, you had, yeah, that one there.
Yes.
So my question there was, there's just technicality. So there's these T's and these S's, those are numbers.
Yes.
So you're saying that there's a bijection between those two things, between the measurement in one.
When you go from.
No, sorry, no, not that one. You had a slide where you relate the call by name and the call by value measurements.
Here.
Yeah, so you say T
yeah.
and T prime are calculable one. So that's, you're suggesting that there's a function from the T to the T, a bijection from T to T prime. And these are numbers. I mean, I'm surprised that that function works just on the T and the T primes and not on the whole derivation.
No. The functions are using information coming from the derivation.
Okay.
This is a simplification of course.
Yeah. Okay.
If you want to go from T to T prime, you need the information in the derivations.
Okay.
Of course.
Okay. Good.
Yeah. This is just a simplified presentation of the purpose.
And probably will be just information from the encoding of T to TV, right?
Yes, but in order to obtain T prime, you don't only need T, but you need also information which is in the derivation Yeah, because you are looking the way. I mean, the derivation is encoding the evaluation sequence, and so you are looking in some sense in the evaluation sequence.
Okay.
Yeah.
Okay, so we don't have many, more questions. Then let's thank Delia again, and we are going for lunch. Okay.
Thanks for your questions.
Sorry, I'm Santiago. Y just that I went to the hotel. Okay, so thank you for coming. This is the third session of PPDP, okay, and it is an honor to. Well, you didn't write there, but so if you see the program, okay, this is a talk for the 10-year award. Okay, so this is really a paper published 10 years ago that the steering committee of PPDP, okay, decided to give this award. Okay, there is no money. Sorry. Okay, there is no.
That's the first thing my children are.
There is no piece of paper. I can prepare one for you and send it to you. Okay, but but you see, but in the program it appears really as a 10 year. Okay, so we have 1 hour and a half. Okay. But you see, it's as much as you want, okay? Because there's a coffee break after that, okay? So thank you very much. Okay, you can start.
Thank you very much. Yes, so I guess 3 months ago, I got an email from Santiago and others to say that this paper had won the 10-year most influential award for PPDP. I thought, oh, this is really nice. Thank you very much. It's a very nice thing to happen. The only thing is that, well, we've all moved on. I'm not working in this field at all anymore, and nor have my co-authors. So, now I've got to present work that was 10 years old and update it as well, because I have no idea what has happened in the area since. But I'll try and do that. So I'm no longer at Microsoft, I'm at Meta, along with Nick Benson, one of the co-authors, and Jonas Jensen, who he had some of his PhD was based on his work. He's now working at GitHub, and Pierre Evariste is in Paris. Yes. So I'm going to try and give you a flavour of what we did in this paper 10 years ago, and a little bit about another paper we wrote, which was published at Popple, about the logic associated with the work. And then at the end, I'll say bring us up to date a little bit, in as much as I can understand the field still. So here's the outline. Yeah. So firstly, I'm going to rewind, talk about what was our vision for why we did this work, and then a kind of recap. Sorry if people were here 10 years ago, but some of the slides are the same from then, and a little bit of a kind of commentary on, has this stood the test of time? And then, so fast forward, I've had a look at some of the people who cited our work and related. So a couple of highlights, I feel, from recent work on machine code, spec and vec. And I'm going to indulge myself with a little bit of work that I did at Meta with Nick, which I feel is kind of related. I'd say it was a bit inspired by some of this work. Okay, so and do dive in with questions at any point, please. So this was our vision. I can't say that we've realised this vision, but this was it. That we want to build proofs of safety for an operating system running verified code, where you have a kind of end-to-end property that says these processes are isolated simply because through proving correct rather than through some kind of memory protection mechanism. So here's a kind of picture where you have, so it's the idea we have like applications running over the top of some operating system, and everything is verified from the ground up, with kind of proof of the high-level code, and some kind of typed assembly language was the idea we might get to eventually, and checked by Coq in this case. And I think what's maybe still a bit unusual about this work is that we built everything inside the Coq proof assistant. So there's no other languages involved. We model the machine code in Coq, bits, bytes, memory, all that kind of thing, including like instruction decoding and execution. We even generate machine code from Coq. So we have and that's why we say it's the world's most powerful macro assembler. You can write assembly syntax basically inside Coq, and then use Coq to actually produce the machine code and even then run XEs and DLLs. And it was on Windows, of course, because I was at Microsoft. And then we can specify and prove programs correct inside Coq. And obviously, that's the more traditional use for Coq. We built like a separation logic for low-level code. That was the subject of the Popple paper, and various tactics showing that programs meet their specifications. So there's a ton of other work in this space, but I don't think anyone else tried to do everything inside, one place, which was the Coq theorem prover. So why PPTP, you might be asking? Well, if you think of languages as sort of inhabiting a continuum, then there's one end is imperative and machine code, and assembly language definitely falls into that. And at the other end, declarative, well, you could argue Coq is pretty as declarative as you can get, really. It's, terminating, based on type theory, very high level. So our goal was to use this highly declarative language to, like I just said, model and generate and specify and prove programs that are written in a highly imperative language. That's x86 assembler. So why Coq? I mean, it's got a very rich and higher order and dependently typed type system, and that's obvious for a lot of things that you want to model in machine architectures where you want to parameterize over things like bit length. Dependent types makes a lot of sense. It also has a lot of conveniences, which doesn't really relate to its use as a proof assistant, but it means we can actually write assembler syntax actually in Coq itself. And you can write programs inside Coq in a functional style and run them. So that's how we actually generate code from the proof assistant. But of course, I mean, as is often said, it's got a very steep learning curve, but it's addictive, as it's been pointed out. So it was a lot of fun. So here's, I don't know, just kind of curious actually, because who here has ever programmed in assembler or machine code? Okay, so probably more than half. Okay, so this is the assembler syntax for x86, 32-bit x86. What does this program do? I think it's, maybe this is the factorial function. So it's the Intel instruction syntax. There are other variants. There are labels here, so you don't have to write actual addresses in your jumps. There's various other things which don't relate necessarily to instructions, like inline string data and so on. And there are macros. So here there's a macro for a loop, and there's a macro for calling external code. Now you're probably going to predict what I'm about to tell you, which is that this is actually just a definition in Coq, even though the syntax looks like what you would feed into the Microsoft assembler. So the assembler syntax itself for the instructions is just user-defined Coq notation. So Coq has this nice notation facility, basically kind of extending the grammar of the language. And the labels, we're using a kind of high-order abstract syntax to trick to get labels into the assembler code. And macros obviously are just definitions in Coq. So the while macro is just a definition of function in Coq. Yes?
When you say user-defined notation and it's assembler code,
So do I, as a user, have to specify the full x86 assembler code first before I can call it?
We did that.
Yeah, so it has to be added.
It does have to be added, yes. So yeah, I'll come back to that actually later. So that is a bit of a disadvantage, I suppose, of this approach. So not only can we write this and model it and prove it and so on, but we can also use this to generate code. We've got an assembler that is implemented in Coq. So here we've used that assembler to build an executable. So we've even got the format for linkable executables with some standard syntax. And then we say, generate the bytes at a given address to load this. And then compute is Coq's kind of declaration to say, actually run this code. And there, we have to do a tiny little thing which we couldn't do in Coq, I think, which was to convert the hexadecimal into a binary. But that's the only thing outside of Coq that we're using in order to generate this binary. And we run it. There it is. Factorial running. I'm not going to try and do a live demo. I've not even tried to get the source code from 10 years ago of running on this machine. But or we can even, and this was quite fun, run it on the raw metal without even an operating system. So you can link it with the sort of standard bootloader. And at the time I did this, you would probably have plugged a CD into your laptop. So this was, I wrote Game of Life in machine code using Coq and then running on the bare metal. A lot of fun. So obviously what you want to do is then prove something about this. We didn't get that far for Game of Life at least, but in principle we could have done proofs. Okay, so I'm going to now do a kind of recap of the three things: modeling of x86, generating code, and specifying and proving. So start with nice use of dependent types for vectors of length n, basically, for all the different kind of n-bit words that you want, with various notation, some functions. So to compute the, what's this doing? I don't know. It's stripping off n bits off the low bits off a bit vector. The point here is that not only are these things we can prove theorems about, but you can actually execute these things, and that's how we actually built, the assembler and so on. And then write functions to do actual machine arithmetic on these vectors. So this is what's this? This is doing the adding 2 bits with carry and all of that kind of thing. So it's very algorithmic, so we can compute. But then to actually prove things about, like machine arithmetic, it's a bit painful to prove in terms of the bit representation. So, and we've got all these libraries in Coq, like SSReflect is this library of mathematical proofs. So we exploit the fact that the integers modulo 2 to the n there's an isomorphism between them and our bit vectors to actually compute in one place but reason in the other. So you can see an example of that here, which is showing that addition is associative. And this is a little proof script from Coq that does that, exploiting the isomorphism, and then using some existing lemmas from SSReflect, the maths library, that give you associativity, say, for addition. Okay, so now we're going to talk a little bit about how we then model the x86 ISA, instruction set architecture itself. Machine state is pretty straightforward. There's some registers, there's some flags, and there's memory. We only modeled sequential computation, so didn't have to get involved in weak memory models and all that kind of thing. But other people have studied that. And this is just a subset of x86, but enough to demonstrate things like factorial Game of Life and so on. So the x86 is kind of notoriously complicated. There's a lot of, especially the instruction formats, but I'd say Coq was pretty good at abstracting enough that you don't have to kind of just enumerate all variants of instructions in some big data type or something. You can parameterize on various things like addressing modes and so on. So then we need to model instruction decoding, because unlike some other work where you start at the assembly level and you're modeling that like you would model a programming language with a sort of abstract syntax tree, we want to start with the binaries. We want to actually be able to give an interpretation to machine code on the metal. So we have to model instruction decoding, and we did this via sort of a little monadic, some shorthands. So you can see it's literally we're sort of switching on the byte that it's just read from the memory and then reading some more depending on what instruction it is, and then producing the sort of abstract syntax tree of the instruction. And then instruction execution was just like a partial function from states to states, also using a kind of monadic style. And putting it together, we just have this state-to-state sort of transition function that, what's it doing? So it's probably worth just stepping through this. So it's saying pick up the instruction pointer from the register state, that's old IP, do the instruction decoding, which gives you back an instruction and the new instruction pointer, set the register with the new instruction pointer, and then actually evaluate the instruction. Okay, any questions on that? No. Okay, so now I'm going to talk about the other side of things, which is generating x86, not reading x86. So what you saw there was using some kind of data type in Coq to represent the instructions, but it's a bit painful to construct unless you're doing, you're building a compiler or something. If you actually want to hand write this stuff, then it's nice to have something a little more high level. So we mimic like you saw, Intel instruction syntax using the Coq notation feature. So this, Microsoft or Intel standard for writing x86 assembler translates just using the notation feature into this construction of some data type value. And then you want to be able to build programs which are sequences of instructions, but they also involve like labels, abstract labels, and we had a kind of higher order abstract syntax like trick to write those so that you, I think, it's a lambda, is it? Yeah, there we are. The body of this thing which gives a label is actually a function. And so now we have to implement instruction encoding, and I'll come back to this because obviously we want these to agree, and it's a bit painful to write this twice. If you look at the 2,000-page Intel ISA, then they'll have these diagrams of instruction formats. They won't talk about how you actually implement encoding, and obviously the chip implements the decoding, but we had to do both sides. So this is again like a monadic style. It's just sort of switching on this abstract instruction and then literally writing out using the monad the instruction format. And then using this encoder, essentially we're implementing an assembler that determines some assignment for the labels that works. And then obviously we want to prove some kind of round trip theorem that says that the instruction decoding is an inverse with respect to encoding. So now we've got a way of writing instructions. We can build little abstractions just using Coq definitions. So this is, what is this? This generates some code that computes the maximum of 2 registers. And you can see it's using the label syntax to do the sort of jump over the move instruction. And here's another one that does a kind of if then else. And the macros can obviously be parameterized by anything you like. So could be by values or registers or whatever. Yeah, so they can use any Coq feature. So here's a macro that's recursive that actually generates a sequence of shift and add instructions to compute, to do multiplication, basically. And I'm using, what's this, natural numbers in Coq as the number of bits. So we took this further, and there's much. I'm not going to talk in detail here, but one of the co-authors, Pierre-Évry-Jagon, did this work on regular expressions. So you can go all the way up to some high-level DSL, a very declarative thing, and use Coq to sort of make the connection between the high-level DSL and the underlying implementation. So what he did was compiled a regular expression to a DFA. Using this was quite nice because it was just using an off-the-shelf, if you like, existing Coq library and proof of correctness, and then he did the translation from this DFA down to assembler, and so you've got the whole kind of chain. Okay, so now I'm going to move to the way we use Coq to build a logic to specify and prove correctness of machine code. So this is mostly covered in another paper, which was the same year. So the first question that kind of arises is, why do we need a special logic for machine code? So it's common, when reasoning about high-level programs to use something like Hoare logic, where you've got a command and then a precondition and a postcondition, the sort of well-known Hoare triples. And in the last 20 years, we've got separation logic that makes reasoning about pointers tractable. So can we just take this and use that for machine code? Well, some people have done that, but it suffers from a couple of things. Well, firstly, machine code programs don't really finish. They just keep running. So there is no postcondition. And also, code and data are all mixed up. It's not structured. There isn't sort of structured control flow like you would use Hoare logic for. And code can be kind of higher order, where you've got code pointers. And so what we did instead was, instead of a Hoare triple, I've seen it referred to as a Hoare double, where you kind of have, there's a precondition, but there's no postcondition. You're just saying this code is safe to run under this precondition, and that's roughly what we did. And you can recover Hoare triples for actual structured code by a sort of derivation, a kind of CPS-like thing. So, yeah, we built an assertion logic, which is like a predicate on states. This is like a lot of work that was being done at the time on separation logic. And we had to build in various technology that was also around at the time, step indexing, to get, these, I don't fully understand all of this stuff actually, but later and frame connectives. But then the safety specification is in a kind of continuation parsing style, and you'll see that in a second. So here is actually a Hoare triple defined in terms of our safety predicate. So basically this is saying if it's safe to execute code where the state begins with the instruction pointer having J in it and some precondition Q, then it's safe to execute code that precedes that. So that's why it's a sort of CPS-like thing. So this is the precondition, P, and this is the postcondition, Q. And the instruction pointer starts at I and ends up at J. And this is then saying the code is actually here between these two pointers. So we've defined, just in terms of this kind of Hoare double, we've got a standard Hoare triple just as a derived thing. And then you can derive rules that in separation logic you'd be familiar with, like the frame rule, just as a consequence. So here's an example of how we would use this to give to specify what it means for a particular instruction. So this is the push instruction. So push a register onto the stack. And you can see we've got a kind of precondition where the stack pointer starts at SP. And this is what was at the top of the stack before running the instruction, and then afterwards the stack pointer has been decremented by 4 and it now points to the value that we've pushed from the register. So you can and then you prove this lemma basically using our semantics. But the idea of lemmas expressed this way extends not just to instructions but to, say, macros. So here's the macro we had earlier, which was the sort of multiply by doing multiple shifts. And this is a lemma that says how that behaves in terms of precondition and postcondition. So here's an example of proving a very, very small program. So this is swapping 2 registers using exclusive OR, the exclusive OR trick for swapping registers without using a temporary. So 3 exclusive ORs, and this is the spec, basically saying that there's a precondition where registers are this way around, V and W, and then postcondition, they've been swapped, W and V. And we have to say something about the flags because we're going to mess up the flags by doing these instructions. So, and I'm not going to go through this script, but this is the Coq proof script for showing that spec is met. So we have a little bit of automation, so some tactics in Coq, but you do have to do quite a lot of manual proof. Probably down the bottom here, we're even using, well, some of these would be lemmas that we'd probably proved using this mathematical library SSReflect. Okay, so that's a quick overview of what we did with the logic. So now I'm going to sort of look back a little and say, well, what were the limitations and what has happened in the last 10 years? Now, I don't know what's happened in the last 10 years. I just had to look at the people who've cited us and ask around a little bit. So I'm just going to select like 2 or 3 things that I think are kind of interesting that have happened in the last 10 years. So obviously the limitations, there's some obvious limitations. One is that it's a rather small subset of just 32-bit x86. So it's not comprehensive. And the other is that we had to construct this thing very much by hand. We might have got it wrong. So how can we trust this thing? It's not authoritative. I think we did consider, how we might test the spec that we got against actual execution, but we didn't get that far. You just have to trust it. So one thing that's actually happened in the last 10 years is domain-specific languages for specifying the semantics of processes. That's the ISA. So when we did our work, I think this was just starting. There was a language called LEM, but if you look in most processor references, so if you take the Intel one, it's 2,000 pages. It's all in English. I mean, there's kind of no formalism there. Other specs are better. So ARM, they have a kind of a way of describing things that looks almost machine readable. And actually people have done that. They've taken the ARM spec and scraped it and turned it into something that is machine executable because it's written in such a kind of pro forma sort of way. But one thing that's happened is these languages have been devised, and the most prominent, I guess, is this language called Sail, which is mostly the University of Cambridge, where you can specify the ISA. And there's now sale specs for various subsets of various processors. And in the case of ARM, they even generate the sale spec directly from the internal definitions. And even better, for RISC-V, it's actually been adopted as the way they are going to, specify the processor. So that means we could use that rather than having to handcraft stuff. And that's what's happened with, so for example, this is a recent paper from last year at PLDI by some of these folk involved in SAIL, where they've kind of connected all the dots. They've got a model of machine code and a logic, and it's kind of what they call authoritative. It means you can kind of trust it because the spec is the real thing. So this is their kind of, you probably can't see all the boxes here, but this is their high-level diagram. So it is comprehensive in that it's, say, a large subset of x86, and authoritative. You can kind of trust it. And they use some of the similar tech that we used, so separation logic or doubles and so on, similar in spirit. But I think, in my mind, there's still something missing. One is that there's a lot of languages being used here. So there's this language called SAIL. They've got another language called ILA, which is used to describe, it's like a microcode, I suppose, so you can express high-level instructions in smaller units. And that all sort of sits outside what you would call the trusted computing base. So all the stuff outside the box that's got cock inside, you just have to trust. And it's also not clear to me, and I haven't spoken to the folk involved, whether all of this stuff can be kind of abstracted in the way that we've done. So you could build an entire verified compiler, say, or that regular expression DSL, all inside the same system, because they're using SMT solvers and various translations. So it's not clear how much of this stuff can be abstracted, but it's pretty impressive. This is quite good. So the other thing that I'd sort of like to comment on is the encoder and the decoder, which we had to write in this kind of monadic way. It's not really very declarative. At least we proved they round-tripped, but it was pain. The instruction format itself is kind of buried in the encoder and decoder functions, whereas if you look at an actual spec from a processor manufacturer, then they'll describe the layout of an instruction. So here's a paper that I've found does something quite nice, which is what they call bidirectional grammars for this problem, machine code decoding and encoding. So the idea is you specify the instruction format in a declarative way with a little bit of dependent types, because there's lots of dependency in instructions. And then you can derive the decoder in the encoder and the theorem kind of by construction. And it kind of fits into the same sort of flavor as we've got, which is everything's done inside cock. And they've applied it to x86 and MIPS instructions. So if I was to do this work again, I think I might use something like this. Okay, so the last thing I want to talk about is something that I've done since I've been at Meta, because I've not done any of this machine code verification stuff. But I'd say perhaps the way we did the Hall logic kind of inspired this a little. So I've been working on this language called Hack, which is the most used language at Facebook. It's not used anywhere else, really. And it's derived from PHP. So PHP is a disaster zone of a language, but unfortunately, Meta had a million lines of code in it. It's what powers Facebook, basically. And they needed to do something about the various disasters. And so they kind of evolved it into this language that looks more like C# or Java or a sensible language. So that's what I've been doing, working on its type system. It has an unusual feature, which is not the worst of the features, really. which is that locals aren't declared. They don't have lexical scope. I don't think that's as bad as it sounds, but it would be nice to infer types for them, make them safe, and to do that, you need to do this in a kind of flow-sensitive way. So I'll show you some examples in a second. So we need some quite rich types to do this. So we use union types at join points in the program, and we also use intersection types when we refine the types of locals by testing them for like runtime tags. So here's an example of using a join point. So here, this is a function in hack. It takes in a Boolean, and it returns mixed, which is just top in hack. And then it branches based on this Boolean, does some, I don't know what it's doing, it's doing some assignment to this variable x. But you'll see that when it leaves the condition, the variable is either an integer or a string. So, and then when we return it, then, well, you can return anything, but the point is that internally, hack will actually give this variable, this union type, into a string. Now, that's straightforward enough. But what about more complicated control flow? So hack has the usual stuff you would get from C-style languages, but with exceptions. So we've got catch, we've got finally, we've got break, we've got continue. And you can have something really quite complicated where variables get assigned different types, and what type they actually have depends on the control flow. So, in fact, there's an error in this program. It might not return a string. Let me see. Anybody see where that might be? Ah, yes. If you enter the loop and I is smaller than 5. Yeah, so when you break, it'll break out the loop and S will have a Boolean in it. Yeah. So, and when in 2016 at least, hack was kind of broken, it managed to do join points, but some of this stuff just was not sound. So how do you solve this problem? So this was what we did. The idea was that at any program point, there's kind of a fixed number of possible continuations. There's the next statement, the usual continuation, but there's also the break continuation, so to the end outside the loop, the continue continuation, and then catch and finally for exception handlers. So just to show how we handle that, I'm going to take a very tiny subset, just 4 or 5 slides, to show you how we do this. So here's a little subset of hack. It's got expressions, it's got statements, the usual kind of looping constructs, but breaking and continue as well. And it's got subtyping. And for typing of expressions, do the usual thing, define a context for the locals, and then define a typing judgment for expressions. Fortunately, expressions can't now at least make assignments, but they used to be able to, so we had to deal with that at one point. But we killed that off. Now to type statements, and this is where we use continuations, we define another context which contains the possible continuations. And the continuations are typed with how the locals would be typed when you jump to that continuation. So, and if anyone is familiar with the work from years ago of typed assembly language, they had a similar idea there. So here we've got the next continuation means it's safe to move to the next continuation with an integer in variable x, but it's safe to break with variable with x containing a string and so on. So the judgment for statements then includes these two contexts, and you'll see the similarity with what we did with the x86 logic, which is it's safe to execute this continuation under this bunch of locals, or in x86, any state satisfying some precondition. And then we can implement that as an inference, inference algorithm for inferring the types, because you don't have to put types on locals in hack. In fact, you're not allowed to. And it's essentially computing like the weakest context such that this will hold. Okay, so coming to my conclusion slides. So there have been a lot of advances, most of which I don't know about, since 2013. But one thing I still haven't seen actually is using the sort of cock for everything, where you're doing it all inside one environment. I mean, we used to talk about this being the sort of ultimate IDE, where you write your code, you specify, you model it, prove all in one place. And it kind of encourages this modular use of little languages and just building DSLs and very fine-grained abstractions. Okay, so my last slide is a sort of personal one. So I was sort of thinking, I started out my computing career, if you like, when I was a boy, many decades ago, programming in machine code. So cue embarrassing picture of me from a very long time ago. So my first experience was Z80 machine code, assembled by hand into hexadecimal. And here I am, doing this in a theorem prover and cock now. Okay, thanks for listening.
So I have one great talk first.
It's on.
Oh, okay.
For recording purposes.
Okay. So I have one question about your use of notation, right? This approach seems to rely heavily on cock notation. What is your experience with that, and how difficult was it to hack that syntax into the notation mechanism?
It's a horrible hack. Yeah, it's only just possible, and I think it was a kind of trick. But I can imagine it would be nice to have a better thought out way of just switching into your user own, a new grammar, and providing a full, parser or something, rather than just using these notation tricks.
So last year Splash, I made a workshop called Unsound, Sources of Unsoundness in Verification, where basically one of the kind of conclusion, okay, not mathematically proved, but informal conclusion is that when you extend whole logic with either dynamic dispatch or first-class functions, it's very, very tricky to not make it into an unsound system. And you have mentioned that your Hoare couples, one of the things that you were trying to solve was a dynamic code pointer, basically. Yeah. So can you expand on how you did it soundly?
I think I'd have to refer to my co-authors for details there, but look in the Popple paper, because it does talk about higher order specifications, and in fact the other people doing similar work, like the Islaris work, I mean they do higher order stuff as well. So for example, they do kernel level stuff like installing exceptions in exception tables and all that kind of thing. Yeah, I don't know whether I've got an example here of that, but yeah, it is tricky, but yeah, I think it refers to the paper.
More questions? I have a couple of questions myself. Thank you very much for the presentation. Okay, I think that was very inspiring. Okay, and so I have a couple of questions, comments, just to think. So one of them is this kind of gap, right, between the formalisms and the actual implementations, or the more industrial things, okay, something like that, okay, so that there is really a gap, and at our level sometimes it's difficult to make it clear whether there is still a gap or not between representation, things like that. So that's like one question, okay? And the other one is that, would you consider your paper like ahead of time, or do you think that at that time it was already like a movement towards these kind of things?
So the gap, I think, I mean, the paper that was at Popple was, the title was it high-level types for low-level code, I think, something like that. And I think that's the point, that you've got these, you can have quite expressive types that describe very low-level code. So it's the abstraction that gives you that. So, and you could see that with the regular expression example. We used some off-the-shelf, high-level thing in Coq that compiled regular expressions into DFAs with a proof of correctness, and then we took the next step of then doing the translation into assembler, and the whole thing is proved from top to bottom, and the theorem that connects them is quite abstract, and you don't need to worry about the machine code. What I don't know is how, what we never got to work out is how to scale this. I mean, there were tiny programs. To do this for an operating system, you absolutely need a bunch of automation. And my feeling is that then you would lose the ability to abstract. Well, because you'd be proving.
This Australian company, right?
Oh yeah, yes, SEL4, yeah. But I don't know. There have been advances, and so the next question was, was it ahead of its time? No, there was a bunch of other stuff going on at the same time. So people like Magnus, Myrene, and others were building models of processes and building separation logics. I think the Popple paper did this. I mean, the thing that I can't explain because it's not I'm not the expert, but the higher order code pointers, that was novel at the time. That was ahead of its time.
You have more expressive power in some sense using Coq or many of these formalisms, to express capabilities or features of these underlying languages.
Yeah, well, I mean, I think the Popple paper was almost independent of Coq. It was the logic itself that was an advance. But there were a lot of people using Coq in a similar way. I mean, I'd call out what's his name, Adam Tripala, and his Bedrock work. He was kind of using all the abstraction facilities of Coq to do advanced programming. Yeah.
Okay, thank you. Any more?
This is perhaps my fairly limited awareness of what's been happening in this space, but from my understanding, I think a lot of work in the past 10 plus years sort of focused on doing, I'm thinking of this kind of verification of very low level aspects.
Yeah.
So like Peter Sewell's group, right, they worked a lot on Isabelle, right, rather than Coq. And I was wondering if you could comment on perhaps why they chose Isabelle rather than Coq. Is perhaps Isabelle better suited somehow for a bit tongue-in-cheek, but
they tend to. Isabelle has more automation, I think, but it doesn't. Yeah, but it doesn't. I mean, I think it's habit as much as anything. There's only one theorem prover you can hold in your head at one time, really. But Coq is more expressive as a language because it's got dependent types, and that makes it very suitable for these very parameterized definitions. So some of them, yeah, I mean, if you look at some of the work on modeling of machine code, there'll be more lines of code because they have to describe every variant of the instruction separately rather than being able to abstract out the commonality in a way that ends up becoming dependent. Yeah.
So you mentioned the problem of being the authoritative authoritative spec, and some of the follow-up work which was that, but then there was this blow up in terms of what is outside the trusted computing base, right? So do you have any answer, like vision of how to reconcile these like conflicting constraints in a way?
You mean the fact that even though the spec is authoritative, you're then using some untrusted
you have
tooling
to have a complicated tool chain. Whereas in your example, everything was in Coq, but then you relied on. You already said you put it to the limit, the notation and stuff. So maybe that doesn't scale to a real thing either. So what would be the right approach there if you want to do it?
I think that's still being explored. I mean, the Islaris paper does talk about the limitations, and it does talk about this issue of having to trust their translation, trust this SMT solver. I mean, they do a little bit of translation validation rather than verification, I think. But then I kind of think if they're doing translation validation, this is my question really at them, I should go to them, I guess, is how do you abstract that? Because they're validating a particular translation of a particular piece of machine code, not the output of a compiler or something. I mean, whereas ours, in theory, could connect to a verified compiler. But yeah, I don't know what you do about them. So I mean, they have this interesting observation, which is that if you try and model the whole of something like x86, then even giving the semantics to a simple instruction is like hundreds of lines, because it all depends on various configuration flags and stuff. And is it running in kernel mode? Is it running in user mode, etc., etc.? And there's like address translations and all sorts of stuff going on that we don't have to worry about because we've abstracted away from that. But if you want to do the whole thing, and what they do is they have something where they kind of that Euler piece of the diagram, it specializes the instruction for the particular kind of configuration that you're running it in. So you don't see these hundreds of lines. It boils down to something much smaller. But again, you've got to trust that. Yeah, I don't know.
To expand on this discussion a moment, in general, all of this work on verification tend to be about chains of trust. Like, for example, if Coq is actually unsound and you can prove false, of course, none of your work. But proving false in Coq is so valuable on its own that once you have verified something from a set of assumptions, what you have really done is to say, either I have done it correctly, or another of those big important things was broken, and finding that out is also exceptionally valuable. So that's where you can put layers of abstraction somewhere where, for example, to put it at a completely different level, you can say, oh, look, I have a JVM or a VM in general. I can assume that this has a specification, and I can prove the correctness of my code, assuming that my virtual machine followed the specification. And again, if the VM is broken, sure, your code is broken, but if your code being broken proved the brokenness of the VM is still very valuable. That's how you build value in those verification settings. Anyone else?
Yeah, so we still have time until the coffee break, okay, because it's at 3:30, okay. Thank you.
Thank you
okay, for your
inviting
talk.
me.
Okay, so welcome to our last session today. We have only 2 papers. Okay, remember that tomorrow at 9 we will start. We will continue. Okay, with another session. So, the first talk, okay, by Gautier, right? So, please, whenever you want.
Yeah. So. Thanks and hello everyone. So I'll be talking about type-directed program transformation for constant time enforcement. This is a joint work with Frédéric Besson and Thomas Jensen. But first, let me put a bit of context. So I'll start by defining what side channel attacks. So we call side channel attacks the kind of attacks that does not uses the algorithm per se to gain information, but more uses physical property or quirks of the implementation of the algorithm. 2 well-known examples are power analysis, which uses the power consumption of a machine to deduce information and secrets on the system, and cache attacks, which use the result of whether the result of an access is a hit or a miss in the cache to deduce information still about the system. One specific kind of side channel attack that we will focus in this talk is the timing attacks. So these are simply side channel attacks that use time as an attack vector. So mostly the execution time of a program. A simple example would be just a branching on a secret. In one branch, we wait for 100 seconds. In the other branch, we just skip. Obviously, if we can look at the execution time of this program, we can deduce the value of the secret. Fortunately, there is some mitigation possible. The first one is to take extra care when programming. So you have to take into account any possible leaks while designing the algorithm and while doing the implementation. That's a bit tedious. Another one who seems kind of obvious when looking at this example is we can try to balance both branches. So if we had a wait 100 in the else branch, whatever the value of secret is, the execution time is the same, and there is no issue. That's a bit helpful because it has been proven that if we combine timing attacks with power attacks, this solution doesn't work anymore. And one only real solution is left, that is to transform the program to abide a certain programming policy, which is the constant time policy. So as I said, the constant time policy is a programming policy to defend implementation against these specific types of timing attacks. It is based on 2 constraints on an implementation. First, we shall not make any control flow decision using secret data. The intuition is kind of obvious. We just have to look at the previous example. If one branch is unbalanced from the other, doing the choice between branches on a secret will leak this value. And the second constraint is no memory accesses using secret data as index. That's a little bit less obvious because it is not immediate. It is due to counter cache attacks, notably, which will use the time taken to get the information back from the cache to reduce the information on the secret. To enforce this constant time property, we have multiple solutions. So we have 2 solutions which are based on guaranteeing that the program is constant time. So first, we can use a verified compiler to prove that the compiler preserves the property of constant time. So if we're able to prove that the input program is constant time, the output one will be too. And the second possibility, which is often coupled with the first, is that we can prove directly that a program, whichever source or compiled, abides by the constant time policy. Both these mitigations have an example, and I have 2 citations here, which show that we can preserve constant time when compiling C, and that we can check that an implementation is constant time fairly easily. The other category of mitigation possible is the program transformation. So first we have the balancing that I have shown just earlier, and well, it doesn't really work. We can also use program repair which is that we will transform the program directly in its form, so it will not pass by an intermediate language or go from source to compile, but stay in the source form. And the final category, which is the base of this work, is program transformation. So one good example is FACT, which uses a type system to compile any program typeable by accepted by the type system into a constant time equivalent. So to present a bit how this talk will go, I'll now present the usual tools used by most of these possible mitigations before presenting our proposed program transformation and its according type system before concluding, obviously. So the first of these tools is actually an operation that we use to enable ourselves to make a choice while being constant time. So we define a constant time selection, which has the same semantics that the ternary operator. So that is that if the guard C is true, then the CT select is equal to E1, else to E2. It's just a conditional in an expression. And we have the property that this particular operation is constant time. That is that whatever the value of C is, it does not leak, it takes the same time. It is not just a theoretical object, we can actually implement it. One way to do it is to use bitwise manipulation. So here we have an example, and we can go through one case. If C is true, then E1 and C will bulge down to E1. E2 and not C will bulge down to 0. And E1 or 0 will bulge down to E1. And it's exactly the same for E2, C, if C is false, and we have the correct semantics, and it is constant time. Whatever the value of C is, we evaluate both E1, C, and E2. On top of this construction, we can propose some transformation. So if we want to mitigate the no secrets access thing, one way is simply to go through all the array. It's not efficient, it's a bit naive, but it works. So if we make a memory read on a secret, we can instead make a for loop over all the array. And if the index we are looking at is the same as a secret, we make a real assignment, y is equal to t of I, else we just make a dummy assignment, y is equal to y. This only works if the array size are public, so that we can loop through without leaking the size, and if all access are initially within the bounds, because if not, we will not find I such that secret is equal to I. Unfortunately, this is incredibly inefficient. If for whatever access we have to introduce a for loop going through all the array, it's tedious, and it's even worse for complex expressions. So, for example, if we make an access on a memory access, while using a memory access as an index, we have to nest 2 of those for loops, and the complexity goes up fast. So that kind of settles how we can transform memory access. The other constraint was to secretly branch on data. Sure, we have the CT select, but we can't put a whole branch within one expression. So what we do is that we use the CT select operation to predicate statements. This is the solution most used by current work. And if we take this simple conditional, we just assign to X the value L1 or L2 depending of the guard, we can transform it into 2 assignments, each one using a CT select, and each one having the semantics of one branch. So the first one is equivalent to if X is assigned to L1, otherwise nothing, and it's the same for the second one. And overall, the semantic is the same, and because of the constant time property of the CT select, this resulting code is constant time. It does not leak anything. So these are the tools available currently. but, well, some are costly. This one is a bit simplistic. Maybe we could do better. And that's actually what we have done. We propose a more permissive program transformation to constant time, which will try to use the array traversal method as less as possible. And to do so, we introduce a new typing system, which both guides and proves the correctness of the transformation. We also have a Jasmine implementation and some experiments. And the reason why we need a more permissive program transformation is because if conversion has some issues. The first one is the safety issues. If we have an access of which the safety depends strictly on the value of the guard. So for example, here, if we do not have the I less than S, we do not have any guarantee that I is within the bound of T, then applying the if conversion will still do the access whatever the value of I is, and we may do an out of bound access. And the second issue is that the if conversion introduces direct flows. So if we had, to our previous example, a memory access in each branch, transforming it will yield something like this for the then branch. That is that we first predicate the assignment to X, so it works, we know it. However, when we try to make the memory access to get the value for Y, X is no secret because it is directly dependent on H, and we leak the value of H. So yeah, our goal was to mitigate these two issues, and we'll start by the second one, not the safety one. So how can we prevent the introduction of direct leaks? Well, we just postpone the introduction of direct flows. So if we take the same example, what we'll do is that we'll define new fresh variables for each branch. So xn, ythen, xelse, and yelse. You can see that the access made on xn is completely secure because we do not have any leak into xn. It's just the value of L1. And what we do to preserve the semantics is simply that we delete the condition, just as in branch removal, and we merge both branches by using a predicated statement. This way, both memory accesses are safe, and the semantic is preserved because we choose the variable which is the correct one, which is the correct branch executed. However, the code that we use as an input, it could be a bit smarter because we are doing the same memory access in both branches. What if the developer was trying to optimize and move it out of the scope of the conditional? In this way, we will have a kind of the same problem, that is that we are merging the statements too soon, because what we do is that we will merge both X that we have defined, and then only make the access on X, thus leaking the value of H. To prevent it, what we do is that we simply delay the predicated statement until after the memory access. Doing this like this doesn't work because we make an access on X and we only define xn and xelse. This doesn't make any sense. So what we do is that we rename Y also. And we also merge the value of ythen and yelse into Y. So what we do in the general case here is that we identify a leaking condition of a conditional, leaking continuation, sorry, of a conditional, and we wait until the end of this leaking continuation to introduce the merging statements. And thus, with both the delayed if conversion and this scope increase transformation, we should be able to transform any secret conditional away. Remains the problem of safety. So, for a reminder, the issue was that executing both branches may cause out of bound excesses. To prevent that we access any index out of the bounds, what we do is that we simply add dynamic checks. That is, if we have a memory access on index I, instead we do memory access on if I is within the bounds I, else 0. So this way, it is always within the bounds. Because our programs are initially safe, we know that Y in the correct branch is always within the bounds, so it does not change the semantics. And if it is the wrong branch being evaluated, the transformation is smart enough to ignore the statement anyway, so it does not have any impact. We can combine these three transformations to obtain a final transformation. So the idea is that we will loop for each secret conditional. We'll find the secret conditional and identify its continuation. That will use scope increase to move the leaking code within the conditional. We'll apply our dynamic checks to ensure that safety will be preserved when we remove the conditional, and we apply, finally, the relative conversion. And we repeat this one while there is at least one secret conditional. So the idea is that we will remove one secret conditional at a time. There is only a finite number of secret conditional. This will end, and no secret conditional will remain in the final program. And thanks to the relative conversion, we also remove most of the secret error excesses by removing the conditional this way. And to, just in case, we still apply a path of error traversal to ensure that there are no secret accesses left at all. Yeah, and so because we have no secret conditionals and no secret accesses, the resulting program should be constant type. To actually do that, and more than anything prove that, we define a type system. So firstly, the first problem was to identify this leaking continuation and know if there are any secret conditional left without having to pass through the whole program. So to do so, we annotate programs with two sets. The first set, G, is a set of secret conditional within P, so simply the set of guards. And R is a set of conditional leaked by P. So to define this set, we use program points. So if you can see here, we uniquely identify each conditional with a program point. And this set are a set of program points. And so G is a set of conditionals contained with the program. And R is a set of conditionals whose value is leaked by a statement. So if we still take a look at our example and try to annotate it, the first step would be to annotate the memory accesses. So they contain no guards, so G is empty, but they leak the value of X, which is dependent of H. So R contain only P. And if we annotate, the whole program, we have the same leakage, but we also have that the program is the conditional P, so it obviously contains the conditional P. And to identify the leaking continuation, what we do is we find the last statement which leaks P, and by taking all statements previous to this one, we are able to contain all possible leaking statements. To do a bit of reminder on type system and mostly secure type system. So the first one was the one proposed by Volpan-Smith. We use two types, high for secret value and lows for public ones, which was a type insensitive type system. So a variable was either high or low and stayed so for the whole program. And it prevented assignment of secret value into public variables. This was a bit too restrictive, so it was upgraded in 2006 to be flow sensitive while keeping the same two types. So now types could be updated through the program. So assigning high values to a public variable would make this variable secret. And what we do is that we upgrade once again this type system. So because our transformation relies on preventing the introduction of direct flows, what we aim to do is differentiating between direct and indirect flows. And to do so, we extend the usual I-low lattice with a new type, I of L, which tracks indirect flows. So a type variable is of type I of L if it indirectly depends on all conditionals whose program point is in the set L. So if we take the first example that we had, the type of X would be I of P because X is assigned within the conditional P. And to be a bit more practical about our type system, the typing judgment for an expression uses two typing environments, one for arrays, one for variables, and yields a resulting type and a set containing all conditionals linked by E. So this will be what will allow us to compute annotations for statements, because, well, for example, if we look at the typing rule for the array red, so the first thing that you notice is that the type system rejects secret accesses. We are needing that the type is an indirect of something, while we can note that an indirect of nothing is simply a public variable. So we just reject if the type is high. And when defining the leaks of the expression, we take both the leaks of the evaluation of the index and the type of the index, meaning that we leak the value of E, which is consistent with all the examples we have seen since for now. And for statements, we keep the same structure. We just add a context, which is used to track parent conditionals. So when we enter a scope of a conditional, we upgrade this context to contain the program point of this conditional. Same, we'll look at this a bit longer typing rule for a conditional, a non-public conditional, sorry. So the first thing that you can notice is about context. What we do is that we evaluate both branches using a context which is augmented by the program point of the conditional. We also update the set of conditionals to contain this one, because obviously. And note that we do not leak the value of C like we did leak the value of the index, simply because we are sure that we could transform away the conditionals anyway. And so this type system, using annotation, has an interesting theorem. That is that if we take a program P, which is well typed with a low context and empty annotation, then the program is constant time. This is easy to intuitionate because if we do not have any we do not have anything in the annotation, that means that we do not have any I conditionals. So that means that there are no secrets possible to do array accesses on, and we do not have any I conditionals. So yeah. And we can also use this type system to have a guarantee on our transformation. That is that if we have a program P well typed and a program point P within the program, then transforming the program P by removing the conditional P, that's a lot of P, will yield a program that is also typable, but that has a guard annotation, strictly less than the initial one. So we have removed at least one conditional. And the same reasoning as earlier, there is only a finite number of conditionals, so we end up by having no conditional at all in the program, so we tap without annotation. So by chaining sufficiently our transformation, we end up with a constant time program. So yeah, that is the conclusion. All programs can be constant time, well, if they are writable in our syntax. And even though I didn't talk about it here, experiments showed that the overhead is often mitigated by optimization. We introduce a lot of temporary variables, but compiler are smart enough to remove them because they are just single assignment. And for future works, the idea is to experiment with real-world example, but mostly to extend the scope of a language. So by handling function calls and looping out secret value, which we do not do here. Thanks for listening.
questions?
So you mentioned.
So in SPLASH, they are recording all the talk in all the places. Okay, so the microphone is just for the recording.
Okay. You mentioned at the end that the compiler might then do some transformations and optimizations. How can you be sure that the transformation the compiler does is not the compiler is not going to undo what
if
you've
we
done?
if we use a standard compiler like GCC, then we have no guarantee. However, we also tried using CompSort, which has been proven to preserve the constant property, and Jasmine, which is a compiler built for that, and which is the compiler we use for our implementation.
Okay.
So in the general case, it does not work, but using specific compiler, we can have the guarantee that the property is preserved.
Okay, thank you.
Any other question? Yeah, I had the same comment because of the. Yeah. Well, so indeed, I was going to ask you about the next steps, which is indeed what you wrote in the perspective there. So can you tell us a little more? So I was expecting some experiments. I mean, maybe not tables, but some experiments. Yeah. So it's a pity that you didn't include here. And I'm not sure, I don't remember if you had in the paper or not.
There are some in the paper. We actually did experiments with some simple encrypted programs. Yeah, we found out that the result is constant time, and that the overhead is at intermediate level quite high. We are like our exponential is the number of variables, but after optimization passes, there is a 1 or 2 offset between the original program and the transformed one. But that's all the point with the experiment on real-world example, which will allow us to see more if this transformation really introduced lots of overhead on it.
Yeah, indeed, and that's the thing that I wanted to ask, in the sense that I mean this graphing, the algorithm kind of thing that you had, right? So the thing is that in real, in long examples, let's call it that way, right? It can be really, I mean, just the product transformation itself can really take a lot of time.
Yeah, well,
it depends on the complexity of the program. So that's why I think that you need experiments in some sense to
yes, and we did on nested conditionals, and it is always linear in the number of conditionals, whatever the structure of the program is. So,
yeah. Okay. Any more questions? No? Okay, so let's thank the speaker.
Okay, so I'm Eduardo. I'm going to present the paper we submitted, Data-Dependent Confidentiality in Dynamic Condition Response Graphs. This is part of a larger project, which is TARDIS. Okay, so when modeling business processes, there are multiple approaches. There are declarative and imperative approaches. Most of them support some kind of security functionalities, such as access control and executor role, so basically who can execute what. But most lack mechanisms to ensure data confidentiality. Okay, so we will focus explicitly on dynamic condition response graphs, which are declarative event-based approach to business processes. Here we have the example of a DCR graph, which models the medical appointment process. There are 4 events: write report, prescribe medicine, emit invoice, and the payment event. there are some restrictions between these events. For instance, the first event to execute must be write report and must be executed by a doctor. By specifying who can execute what, we are already specifying the executor roles, which are there in the left bottom corner. So the second restriction is that a doctor may prescribe medicine, so this event is entirely optional. A clerk must emit an invoice, and after the invoice, the customer, the patient, must pay for the appointment. The last constraint is that every event can only occur once. Just a quick note. In the upper left corner, there is some marking which defines the initial state of an event, which initially excludes or makes an execution mandatory. We'll see that in the following slides. Okay, this is part of a larger process, which also allows to manage patients and doctors, besides making appointments. However, we will focus on the smaller subgraph, subprocess, as it is easier for presentation effects. And we will just use this, the entire process in specific moments. Okay, so dynamic condition responses, as response graphs, as I previously stated, are declarative event-based approaches to process businesses. As such, they are quite flexible when it comes to program acceptance and changing programs, since we only have to reason about pairwise events, pairs of events. This also makes it quite user-friendly. Okay, so the events, one of the two main components of the DCR graphs, are nodes and are stateful entities. As such, they comprise the state of the graph. It is possible to execute events, changing their state and therefore the state of the graph. Events fall into two categories in DCR graphs. They are either input or computation events. If they are input events, they allow for input, the input of external information. And in the case of computation values, they allow to either store or generate new values based on existing ones. Okay, as stateful entities, events store both data and metadata. In the metadata, we have control information, such as whether or not an event has already executed, if it is pending, and if it is included. An event is pending if its execution is mandatory for the graph, for the process to stabilize, to reach an acceptable state. And the node may or may not be included, since DCR graphs allow for the dynamic inclusion and exclusion of events. Regarding data, the only data they store is their value, and it does not make sense to have a value if the event has not executed. In that case, the value is undefined. There is also bit of a hidden information, which is the enabledness, which is if we can or cannot execute an event, but that is calculated dynamically based not only on the included set, but also on the constraints, on the relations. Okay, so at the graph level, we store the state of all events in the marking, which is the tuple between consisting of three sets and a function. The three sets map directly to the Booleans, so it's a set of executed events, a set of pending events, a set of included events, and the final element of the tuple is a partial function mapping events to values. Here, the three events on the right side are grayed out since they are excluded and cannot be executed. They are initially excluded due to the percentage mark on the left upper corner, and the right event report is in the included pending set of events, since it has the bang, which states that the initial state of the event is pending. Okay, so regarding relations, the relations are the edges of the graph. And there are 6 types of relations in dynamic condition response graphs. So the first two, exclusion-inclusion relations, allow for the dynamic inclusion and exclusion of nodes in the graph. Note that the inclusion and exclusion does not immediately refer to, okay, the nodes do not exist. It just means that we do not take those nodes into account when evaluating constraints. Okay, so the exclusion relation establishes that if the event on the left-hand side of the relation executes, then the event on the right side of the relation must be excluded from the graph. This, of course, assuming that G, which is the relation guard evaluates to true. The inclusion relation has the opposite effect. If the event on the left-hand side executes, then the event on the right-hand side of the relation must be included. Okay, so now considering the example, if we execute the write report, we have to first include the write report into the set of executed events. We exclude it from the set of pending events since it has executed, since it was put in the set, and we remove it from the set of included events. This is due to the exclusion relation with itself. But on the other hand, we include the other three events due to the green arrows, the inclusion relation. Note that although P has now been included, it still cannot execute. This is due to the remaining relations, which we will see in the next slide. Another detail is that the event emit invoice is also pending. Once more, due to one of the relations, which is the response relation. Okay, the next two relations, the condition relation and the response relation. The condition relation establishes that an event on the right-hand side cannot execute unless the event on the left-hand side has either executed or is not in the graph, is excluded, and of course the guard evaluates the true. The response relation, on the other hand, states that if the event on the left-hand side executes and the guard evaluates the true, then the event on the right-hand side must mandatorily execute before the graph can reach a stable state. Therefore, event E becomes pending. So now, if we execute the event emit invoice, we Okay, so if we execute emit invoice, we add it to the set of executed events, we remove it from the pending events, and remove it from the included events. The removal from included events is once again due to an exclusion relation with itself, but we now add pay events to the set of pending events due to the response relation, the blue arrow, and now we can pay, we can execute the pay event due since the condition relation, the yellow arrow, has its constraints fulfilled. Emit invoice has executed, therefore pay can execute. Okay, the last two relations are the milestone relation, which is similar to the condition relation, but allows to repeat the wait for an event to execute. While in the condition relation, if the event on the left-hand side executes, it stays executed. We cannot unexecute it. If it is executed, all events that are related to it through a condition relation can execute. The milestone, by requiring that the event is not pending, allows to repeat the waiting. So if there is an event pending and we execute it, it is no longer pending, but we can at a later time re-add it to the set of pending events by using response relation. Okay, finally, the spawn relation allows to instantiate subprocesses and nodes. So this is actually addition of new nodes and graphs and subgraphs to the graph itself. So, for instance, if we execute the event new patient, we get a new patient. If we execute it one more time, we get another patient. Take note that the identifiers are different. We have P1 and P2. This is due to alpha renaming when performing the spawn relation to avoid naming conflicts. Okay, so now we can also execute the new doctor. In that case, we got a new doctor and a new appointment event. And if we execute the new appointment event, we get the whole subgraph, the subprocess that we were using as an example. Okay, basically our objective is that given some sort of API that users use to communicate with the graph, for instance, a REST API, we can compartmentalize information and therefore stop users with insufficient privilege from accessing secret information. For instance, an admin can access anything, but a clerk can only access billing information. For instance, a doctor has access to the report and the prescription, but not to billing information. A patient has access to everything, but unrelated patients and doctors, meaning that this is not the appointment's doctor nor the appointment's patient, cannot access anything. Okay, so to accomplish this goal, we resort to dynamic value-dependent information flow control. So we basically label events and then monitor data accesses and event execution. So information flow control relies on a security lattice, which is a partially ordered lower bounded finite set of security classes together with a list upper bound operator, and consists in tagging data and then tracking data throughout the system and painting the values resulting from computations involving that information. Then we just have to stop what we deem as illegal information flows, information leaks. Okay, so this is the lattice we use. It's a value-dependent lattice, which means that the labels are parameterized with runtime values. This allows for richer information flow policies as it allows for individual security compartments. For instance, if we use a non-parameterized label such as clerk, every clerk shares the same security compartment, and therefore every clerk can access every clerk's information. So if we use the single label patient, a patient could access other patients' data, and we do not want that. So therefore, we use value-dependent information flows. Okay, one small detail is that the information flow labels here match the access control roles, the executor roles, but this is just a small detail. It is not mandatory, it is not always the case. We just did it like this because it made sense in the context of our example. Okay, the lattice we use still has one small problem, which is, well, it is so good at compartmentalizing information that now we cannot share information between a doctor and the patient, for instance. We could, but we have to define those security labels, and that would be a bit bothersome. So we use a power set lattice, which allows to use as security labels sets of labels of the security lattice. It respects the original flow, so we get what we want. We can now create a security compartment that allows to share information between a specific patient and a specific doctor, for instance. Okay, now that we have labels and can monitor the events, all we have to do now is monitor the communication interface, and whenever an unauthorized entity, or that is an entity with insufficient security clearance tries to access security data, we just have to stop it. Okay, at first glance, this might seem okay, but there is a small problem. This handles explicit information flows, which are information flows that result from direct operations, such as assignments, in this case, read operations. We still need to address implicit information flow leaks, which arise from the control structure of, in this case, a process. Okay, basically, we have identified two types of implicit information leaks. Well, they are all implicit information leaks. We just made that distinction because one is trickier than the other. It's not so explicit, although they are implicit. Okay, so the first type of information leaks, implicit information leaks, results from changes in the marking of an event. So if we have two events, one secret event which is initially included, and a second event public, which is excluded, and if they are connected, related through an inclusion relation, as is the case, if we execute the secret event, we enable include and enable the public event. So what we have here is that at this point, a user, an entity that could access public events was not able to see anything. There's nothing there. And after the execution of event 1, it can see that there is a new event, a public event that is now available. So it can, that entity can infer that there is some secret event and that event was indeed executed. So we cannot have secret events changing the marking of public events. Okay, the other type of implicit leak, which is a bit trickier, is when a secret event enables or disables a public event. This does not necessarily mean that there is a change in the marking. For instance, we have those two secret events, event 1 and event 2, related through an inclusion relation, and with event 2 initially excluded, and event 2 has a condition relation with event 3. So the condition, just to remind, the condition relation defines that the event on the right-hand side, for the event on the right-hand side to execute, the event on the left-hand side must either be excluded or have executed. In this case, it is excluded. However, if we execute event 1, event 2 becomes included, and therefore it is taken into account when evaluating constraints. Therefore, event 3 becomes excluded since event 2 is included and has not executed. So in this case, we have once more that an entity capable of observing secret public events, at one point it sees one public event, and then after something that he doesn't know, but he can make some assumptions. Okay, there is an event that executed. He stops seeing it. So we also cannot allow for secret events to enable public events. Okay, so this here takes us to the first of our results, which is the dynamic information flow monitor. Just to be quick here, delta prime, which appears first, is the security label of access data in E, and delta is the security label of G, of the guard. It's necessary to take them into account. The PCE is the label of security. The security label of event E. Okay, so basically our monitor defines that one, in the first condition there, that delta prime less or equal than PCE, is that an event cannot access data above its security level. It makes sense. A public event cannot access secret data. A secret event cannot change the marking of a public event. And a secret event cannot indirectly enable or disable public events. So we have both both explicit and implicit flows covered. The second result is our formulation of non-interference for DCR graphs. So basically, it's a typical non-interference. So two graphs given two graphs initially indistinguishable. If we execute two sequences of events which agree on the low events, meaning that the public events must happen in the same sequence and must be the same, our monitor ensures that by the end of the execution, when the graph reaches a stable state, the graphs will remain indistinguishable, so there will not be information leaks. We actually enforce our monitor actually enforces termination-sensitive non-interference, since it does not stop the execution of nothing. It does not halt the execution. It just does not allow the execution of certain events. So they remain hidden, which is not problematic. Okay. Regarding related work, there is some work regarding information flow control and, well, more generally, data privacy in business processes. Agostinelli et al. Analyzed privacy constraints in GDPR and proposed design patterns to integrate them in business processes. This, however, is just a design pattern and does not enforce anything. Tutz et al. Develop a tool to analyze the extent of information leakage in process output. However, once more, it analyzes to what extent information was leaked and does not prevent it. Pulonen et al. Extend BPMN, which is an imperative approach to business processes with information flow capabilities. Barani and Rana employ smart contracts to verify GDPR compliance in business processes. And Accorsi and Lemon develop a tool to enforce non-interference and Petri nets. Okay, to conclude, we presented an extension to DCR graphs, which allows for value-dependent dynamic information flow control, and also formalization for non-interference for DCR graphs. As for future work, we have multiple possibilities. For instance, applying this model to Rigrada, which is another previous work. Resort to either static or hybrid analysis, which we also have some works related to it. And enhance access control capabilities, namely stronger guarantees regarding integrity. Okay, that's all. Any questions?
Okay, I feel I missed the plot somewhere. Could you roll back to your transformation rules?
Transformation.
Yeah, you have A,
okay,
arrow,
yeah.
A prime.
Yeah,
Okay.
here basically...
No, not this one. Further back.
Further back.
Further back. Go. Roll. You need to go to 15 or something, somewhere there.
Okay, easier this way.
Where you define them. Yeah, further. This one.
Okay.
So, for example, so in this context, E is a node in a graph.
Yeah.
Okay.
It's an event.
And you say the node transforms into another node.
No.
That's what this rule says.
No. It changes the marking of the other node. It changes, does not transform it to another node.
Okay, because there is no relation, so E is a node in a graph.
Yeah.
So I would expect this rule to be applied to a graph in which E occurs. And then in that graph you find E prime, and that one is excluded. Is that correct?
Well, the
because
relation...
E prime is free in this thing.
The relation here is, it's just one of the constraints of the graph. So it's part of the graph, and when evaluating the enabledness of an event, we have to take into account this constraint, which is...
Yeah, but the E prime is another node in the graph.
Yeah.
Okay, can there be more than one E prime?
No, basically it's this one.
So
we
it's the context. I mean, I appreciate that you give an abbreviation of the definition. I see that. But the rule itself is unclear to me. So are you saying that, you know, any E prime can be blocked?
Well, as long as it's in an exclusion relation with E, any event can be excluded.
And this is a connected graph? Everything is connected?
Yeah.
Because the example you gave was not connected?
It is, yeah, it's not a connected graph, but it affects all connected nodes. So
the implementation of that rule is that you recursively search to the graph for E prime?
Sorry, just give me a second. So for spawn relation, it's later. For instance, here, for instance, imagine that there was an exclusion relation between patient 2 and disappointment. If we executed patient this P2, the only excluded relation would be this one, which is where to which P2 would be connected.
So there is already a connection between those two
Yes.
nodes in the graph?
Yeah.
And it is through the exclusion rule. And if the first node gets executed, then you automatically change the...
Okay, yeah. When we define the process, we have to both define the nodes and the relations.
Okay. So it is not that the rule is a transformation of a graph, it's in the graph already?
Yeah.
Okay. Okay, thank you.
Any more questions?
If your goal is to model like real-world business scenario, I'm not sure that those must relationship are real-world friendly. Like the customer must pay. What happens if the customer do not pay? That your tool desynchronizes with the reality that is trying to model?
That is just to convey the relation, but
I mean, I don't think there is anything in the domain of business thing that actually must happen. Like
well, here we only accept a graph. A graph is only in an acceptable state if there are no pending events. So by using the must, we convey that either with the bank mark or with the response relation, and that puts an event in the response, in the pending set of events. While that set is not empty, the graph, we cannot say the graph is in a stable state. Is not in an acceptable state. So it has to happen. Eventually, at some time, maybe here, maybe now, maybe 50 years in the future, it has to happen.
Maybe I can add something to that. So the event becomes pending response. That means the process is not finished, cannot finish. If it's distant from the reality, it's because it was badly modeled.
Yeah.
So you have to. So the system that you program doesn't cover that case, but you can cover another event that is someone saying, "Okay, give up on paying," and that excludes some pending event, disappears, and then the graph is stable.
No.
It's about modeling. It's not.
Yeah, but that's kind of what I said. Like the must relation is always an error when you're modeling.
Well, but it's pending. The event becomes pending response, so it's pending on systems, and real systems have events that need someone to take care of those. Yes, so that is part of business processes. Yeah, you have to cover for those cases as well. Yes, in your modeling.
I can still imagine some scenarios where you do have a must that. Oh, sorry. I can still imagine some scenarios where you do have a must, like if you must pass like a credit check before a bank will give you a loan or something. It might not be common, but I think there are some scenarios there.
I just had a small question, okay, because they already asked a lot. So it's somehow related. So I was missing, in some sense, like the connection of these new relations with, so how natural are these? So why did you study D?
Why this set of 6 relations?
Yeah. Why you got interested? I understand that it's part of a project.
Okay, these relations are part of the dynamic condition response graphs, which are not exactly my work.
Okay.
I've just extended them with information.
Okay. So the idea is that you have a former work.
Yeah.
And the idea is that you are going to. Okay. So that was missing in the whole thing. Okay, so in the whole picture. So you had a former work, maybe this Dagrana or
basically
Digrana, and the idea is to extend it to be able to handle this DCR thing. Okay, so that's the reason of this relation. So they come from this other thing.
Yep.
Okay. And also, the other question that I had is that, I have worked on non-interference and the other one, and I understand. I would like to believe, or I would like to understand that these relations are indeed necessary for you to do the non-interference thing.
Sorry, these relations
Yeah, so these new relations are indeed necessary for you to be able to reason about non-interference, about Is that the case?
Sorry, I'm
Yeah.
not understanding the question.
So
The new relations?
No, can you go to the very end of the?
Yeah.
Yes, in the information flow, one more.
Yep.
Non-interference. So I am understanding that these new relations you are adding, you are studying here, okay, are indeed necessary for you to do the non-interference.
Well, the thing is, I do not actually introduce any new relation. The 6 relations that we talk about, so the inclusion-exclusion condition, response, milestone, and spawn are already existing. I did not add anything regarding the relations.
Yeah, no, I'm not. Well, it's not so relevant. We can talk later, but that you are interested in doing non-interference with those 6 relations. That's the point. Okay, so it's not that like 2 different works that they happen to go together. Okay, so you weren't interested from the beginning in doing non-interference with those 6 relations.
I have this language, the DCRs, and I want to be sure that there are no information leaks in the graphs.
Okay, and a very last thing, I got, so I understand it, but I got confused about the E and E prime. Because the thing is, those are 2 different lists of events.
Yes. So basically, the sequence of events just have to agree on the public events.
Okay, but then I was expecting some extra symbol there, like E and E prime are equal some other
that's why they have
equivalent relation.
both have L event, public events, and then they have each his own their own sequences of secret events.
Well, L and H are there will be like the assignments, like the original assignments for low actions and high actions.
Yes, basically.
Or something like that. Okay. No more questions? Okay, so let's thank the speaker. Thank you. We are done for today. Okay. Prepare tomorrow.